communication era in which we all use a lot of internet, etc. And without realizing the fact that we use the fruits of the nonlinear optical phenomenon because we use the saturable absorber, etc. So I'll first initially discuss on the nonlinear optical properties of aluminum doped molybdenum disulfide and its nanohybrid nanocomposite with the reduced graphene oxide, which will be followed by these nonlinear optical limiting parameters for the cobalt doped molybdenum disulfide. And I'll very briefly compare these properties with the doped bismuth ferrite nanoparticles, and finally the acknowledgements. Okay, the nonlinear optical phenomena occur due to the consequence of the interaction of the intense laser field with the material. The nonlinear optical phenomena could be of second order type and the third order type. Second order nonlinear effects include second harmonic generation, some difference frequency generation, optical parametric amplification, and oscillation. We are largely concerned with the third order nonlinear optical effects, where the third harmonic generation, four-way mixing, etc. is important. Especially in this talk, I will emphasize on the nonlinear absorption phenomenon, which we observed in the molybdenum disulfide, and the nonlinear refraction phenomenon, where the refractive index becomes a function of the intensity of the light that passes through the medium. Because of this nonlinear refraction, the laser beam, high intense laser beam that passes through the medium, it can either be self-defocused or if this N2 part is positive, it can be self-focusing phenomenon. In this experiment, basically, because of this nonlinear optical effect, especially the nonlinear refraction, we can have the phase conjugators, we can have the saturable absorber, which are required for this for the production of these high intense laser pulses. We can use this nonlinear refraction for phase and intensity modulation, which are needed in optical communication devices. The nonlinear application, nonlinear optics has nonlinear optical material has a lot of application in laser. For example, we can have new colors being generated when with the use of the saturable absorber. One can have the generation of the pulses, and in the similar fashion, the nonlinear optical materials can be used as sensors and can be used for the data storage, etc. This is the schematics of some application whereby one can see that one can use 3D optical memories using the nonlinear optical medium and the 3D holographic gratings, etc. The nonlinear optical material can also be used for two-photon imaging, etc. And these are also have become of importance as one can generate the entangled states of the photons, which can be used for quantum information technologies. So this nonlinear absorption, as compared to the linear one, is the transmittance of any material depends nonlinearly on this intensity of the light being passed through the medium. The nonlinear absorption could be of two kinds: the reverse saturable absorption or the saturable absorption. Moving. Okay. So in case of the saturable absorption, absorption of non-linear optical material decreases as the light intensity increases. And in this case of saturable absorption, the intensity dependent absorption coefficient alpha is expressed as this, where I set is the saturation intensity. In case of the only presence of the reverse saturable absorption, the intensity dependent absorption coefficient is given by this equation here, where beta is called as the nonlinear absorption coefficient, whose value decides the strength of the nonlinear optical absorption of a given medium. The optical Kerr effect is the cause, basically it causes a change in the refractive index, which is proportional to the intensity of light. And in this case, we can have two kinds of the effect, self-focusing and self-defocusing. For this nonlinear refraction is very important in the case because we have, with the use of the laser in many technological application, it is important to safeguard the detectors and the human from the strong laser beams, and therefore these optical medium which shows this optical limiting effect have become important. In this case of optical limiting, initially when the intensity of the light is not very large, the transmittance remains linear. On the other hand, when the incident intensity of the light increases, the transmittance start decreasing and becomes saturated. So there is some clamping of the intensity, and the intensity does not increase beyond a certain limit through the medium or the material. So with the advent of the graphene in 2004, two-dimensional materials have become important. Okay. Graphene, the dark material, which has nearly zero band gap, is a very suitable candidate for the production of the saturable absorber. Right. But it has a problem that it has a very small band gap. So, and basically we want to have some saturable absorber or the material which shows the reverse saturable absorption for a large band gap or for a large range of the wavelengths of the laser light. In case of the molybdenum disulfide, it has two distinct crystalline phases, and we can see that by controlling the synthesis process, the two phases, that is one the semiconducting 2H phase, on the other hand the metallic 1D phase, can be controlled in the material. The band gap of the molybdenum disulfide is layer dependent. It has a value of 1.8 electron with the monolayer being direct. On the other hand, the multi-layered molybdenum disulfide has indirect band gap of the order of 1.2 electron volt. Another very important aspect of the molybdenum disulfide is that it has a wide spectral absorption range. And for this very large range of the absorption wavelengths, few layers of in general transition metal dichalconates exhibit extraordinary optical and electrical properties, and especially this molybdenum disulfide offers significantly larger optical density compared with the monolayers of other transition metal dichalconides. So there's in order to study these nonlinear optical properties, especially with reference to the optical limiting phenomenon, we have synthesized the pure molybdenum disulfide and its nanocomposite with the reduced graphene oxide, and then doped it with also the aluminum using the sensitive hydrothermal approach. This is the synthesis route for synthesizing the molybdenum disulfide, as well as making it nanocomposite of the molybdenum disulfide with the reduced graphene oxide. We synthesize all these materials, and we found that the molybdenum disulfide, the Pripyat's molybdenum disulfide has the 2H phase. On the other hand, with the doping with the reduced graphene oxide, we have these additional peak appearing at 100 and the 002 for this reduced graphene oxide. The addition of the aluminum does not affect much. With the only is that there was slight decrease in the peak position of in the XRD pattern of the molybdenum disulfide and its aluminum dot nanocomposite with the reduced graphene oxide. We then carried out this Raman spectroscopy, and we observed that the separation of the E1G and A1G, the two vibration modes, one of which the first one, E12G, is the in-plane mode, vibration mode of the, in which only the sulfur atom vibrate within the plane, and the other one, which is the out of the plane mode, that is A1G mode, the separation is to 27 centimeter inwards. If these Raman spectrum is performed at different temperatures, then usually it is found that these peak shifts on either side, and also there is an increase in the bandwidth also. The characteristic D and G bands of the graphene oxide were recorded at these values, and the intensity of the ratio of the intensity of ID over IG is relatively larger, which tells us that there is a high degree of disorderedness and the structural flaws of carbon atoms in the graphene. From these Raman studies, we confirm that the synthesized material sample has few layers of the molybdenum disulfide with the doped graphene oxide, reduced graphene oxide, and the aluminum. These are the FESM images, which shows the flower-like structures of molybdenum disulfide consisting of the large number of self-assembled nanoflex and nanosheet. The nanoflex, the petals of these nanoflex and flower-like structure were of the order of the 20 nanometers. We carried out these UV visible spectra from where we worked out this band gaps. Although this part of the UV visible spectrum does not show the high peak at the 200 nanometer, which is usually present in that case. Also, there is a broad absorption. There is a broad absorption from in the entire 400 to 700, 800 nanometer range, which suggests that the absorption in this the sample is in the entire visible range. We carried out this Z scanning of this sample at the two laser wavelength 405 nanometer, and using this apparatus. These are the open aperture scans, Z scans for these samples, and at different intensities, 3 intensities corresponding to very small powers of 5 milliwatt, 10 milliwatt, and 20 milliwatts. And we noticed that with the increase in the intensity, the transmittance, the depth of the valley, which is the characteristic of the reverse saturable absorption in these samples, increases. As one can see that from the data, I'll show that the depth of the valley in case of the aluminum doped molybdenum disulfide RGU sample is relatively larger. So these are the value with the and these are the values of the nonlinear absorption coefficient beta for a very small or weak laser intensity of the order of few or tens of milliwatts, and with which these materials show the reverse saturable absorption phenomenon. These data were obtained by fitting the normalized transmittance using this graph, which are shown here. The solid lines are the fitted curve for this equation. On the other hand, the dots are basically the observation points. The variation of the nonlinear absorption coefficient, the beta with respect to intensity is found to decrease with the increase in the intensity. This suggests that this reverse saturable absorption phenomenon shown, exhibited by these material does not belong to single two-photon absorption, rather it indicates a sequential two-photon absorption. So as we have seen that the molybdenum disulfide has a larger absorption in the entire visible region. And this 405 nanometer laser used in this experiment has a resonance frequency, which means the system goes to the first excited state, and because of the fact that the absorption coefficient there in the first excited state is larger, the excited state absorption takes place, which goes to some extended band. Okay, from there the phonon state absorption takes place, and as a result, the exhibited reverse saturable absorption phenomena is exhibited by these materials. This is the graph for the optical limiting phenomena exhibited by this system, which shows the optical limiting threshold value of very small value of 13.32 milliwatt for the aluminum doped samples. We further worked out the similar study for the cobalt doped samples, and we found that the RSA behavior, again at the very small powers of the 10 milliwatt, 15 milliwatt, up to 30 milliwatt, and the beta, that is non-linear absorption coefficient value, again showing the similar effect of the change with change in its value with respect to the intensity. So this cobalt doped molybdenum disulfide also exhibited this RSA behavior that shows the two-photon absorption phenomenon, which is assisted by this phonon-related phenomenon in case of molybdenum disulfide. The beta value for the cobalt doped molybdenum disulfide is found to be almost twice as compared to that of the earlier sample studied. This is another very recent result for these materials for the cobalt doped molybdenum disulfide. The earlier result I presented were for the 405 nanometer. These small power values, And especially this at 520 nanometer results, it's proof that this material can be used for as a nonlinear absorber, and as well as nonlinear absorber for this large range of wavelength. This is the theoretical data for the fitting of this close aperture data. A very quick comparison with these results are the bismuth ferrite nanoparticles, which we also synthesize and studied for these their nonlinear optical effect. Okay, there are different nanoparticle of various sizes were synthesized for, and it was found that the nonlinear absorption coefficient beta was found to decrease with the increase in the size of the nanoparticles. We also synthesized this yttrium doped substituted bismuth ferrite thin films of the nanoparticles, and we carried out the Z-scan structures, Z-scan studies for the study of the nonlinear optical parameters, and found that these are also the material which can be used for this nonlinear optical phenomenon. Yeah, this yttrium substituted BF nanoparticle shows the saturable absorption behavior at these powers shown here in the range of 30 to 120 milliwatt with sufficiently large beta values. Okay, yeah, these are last. So the importance of this material is that it is a multiferic material which can be which are used in a number of applications, but we have also detected its nonlinear optical properties and found that these properties has the enhanced values of the beta values. So this is the acknowledgement. Thank you.
The second part of your talk was quite brief, but I catch that you performed very complex investigation of the sulfate molybdenum-based materials. And it is very, very complex explanation. I think it's very useful. Can you say, if we will consider any nonlinear characteristics, say efficiency, the threshold of damage, something other. What do you think are the most prospective for these materials compared to another? What the point, the main properties?
In this molybdenum disulfide, the main characteristic is that it has a very large absorption band.
Can you compare with the best achievements in this field with the help of other materials?
There are other materials, right? So, which is nonlinear.
Yes, there are a lot of materials.
A lot of materials, yes.
What is the best for this kind of?
For this kind of, for example, this graphene is the into a single layer form is a very good saturable absorber. But for that we will need some laser which is
Characterize it quantitatively.
Characterize?
Say,
Oh. We haven't done this comparison yet.
What is idea of doping of molybdenum disulfide doping. For example, aluminium, you use aluminium tetravalent substitution. Cold doping.
Actually, I was rushing through the presentation. The idea is that we want to create defects and defects and free carriers.
Different valency of molybdenum 4 and aluminium 3.
3. So, yes, good.
Will be in the structure.
Yeah, see, with this doping of the aluminum, we will have some free charge carriers in the conduction band.
Oh, I see.
So there will FC kind of the absorption, free carrier absorption also.
Yes, thank you. Good morning, dear colleagues, and my name is Andrei Fedotov, and I would like to present the results of our group at Moscow State University, and we investigated the possibility of generation of ultra-short laser pulses with duration in around 1 cycle of the field, and how the carrier envelope phase can control these processes. So for sure the ultra-short laser pulses with duration around 1 cycle is one of the big subject of laser optics because of variety of applications, such as possibility to control even shorter attosecond laser pulses during tunneling of the electrons from the matter atom, or using such pulses for generation extremely short current pulses, and that allowed to construct electro-optical devices at petahertz scale. Generation of single cycle pulses is still not the routine procedure, and it's possible to count only a few methods, such as using complicated waveform to synthesize such pulses, or using broadband non-collinear optical parametrical amplification, or spectral broadening of driver pulses in nonlinear medium with consequent compressing by different method. And we are interested in the last method, and such a medium we using gas media and nonlinear optical process in waveguiding regime in hollow co-photonic crystal fiber, anti-resonant photonic crystal fiber. So a few words about our experimental approach. We are using a more or less standard TISAF laser system based on a master oscillator, regenerative amplifier, which can produce femtosecond pulses with duration around 50 femtosecond, energy up to 2.5 microjoules, and 1 kilohertz repetition rate. And these pulses pump parametrical optical amplifier, whole bit parametrical optical amplifier, which allows to get tunable radiation in idler and signal waves with tunability from around 1 micron to 2.2 micron with relatively high energy. Overall efficiency of energy conversion from 800 pulses to idler and signal pulses is around 25%. And these pulses are using to pump to couple into photonic crystal fibers, hollow co-photonic crystal fibers, and the main nonlinear optical process is occurring in this fiber, and the structure is showed here. After nonlinear optical interaction, we can get supercontinuum, multi-octave supercontinuum, and multi-octave supercontinuum proposes that it's possible to find extremely short laser pulses. And to characterize such pulses and supercontinuum, we are using the rainbow of different methods and devices, many spectrometers in a different spectral region, and to directly measure, reconstruct electrical field, we are using the modification of spider techniques, so-called XCF spider technique, when the difference from the more or less common spider technique that we make interference not in the frequency domain, but in the space domain. Here just again the structure of our anti-resonance photonic hollow co-photonic crystal fiber, and the diameter of a core is around 70 micrometers, and this diameter is surrounded by 6 capillaries with thin wall capillaries, and the thickness of the capillary of the wall of the capillary is around 500 nanometers, and it's possible to interpret the possibility of wave-guided regime by introducing Fabry-Perot resonances on the thin walls of such capillaries, and it's possible to observe peak resonances. For example, here it's around 1.2 microns, 600 nanometers, and other peaks. But in our regions, the transmission of the fiber is very high, and losses is relatively low, and it's possible. And moreover, the dispersion of the fiber in this region is negative. That allows to expect and to introduce self-compression, soliton self-compression regime for generation of very wide supercontinuum and very short laser pulses. So a few words about physics behind nonlinear optical interaction. When we pump our fiber by the idler wave with wavelengths around 2 microns, the parameter of the driver, the soliton number is around 5. That means that the relation between nonlinear length and dispersion length is 25. That means that on the initial stage of the propagation of a pump pulse inside the fiber, basically self modulation plays first role. But when quadratic phase also accumulated during propagation of a pulse inside the fiber. But when it's broadening enough and passes, I forgot to say that the length of the fiber is around 20-25 centimeters, and the spectral is broadened enough, and on the final stages of fiber, dispersion of the fiber and soliton self-compression starts to play a prevalent role, and we can observe extremely broadened supercontinuum, multi-octave supercontinuum due to interplay, let's say, between two nonlinear effects, self-phase modulation and pulse self-compression. Soliton self-compression, sorry. And theoretical analysis is based on numerical solution of a generalized nonlinear Schrödinger equation, which was proved in our many previous work. And actually, this model consists just a lot of linear and nonlinear parameters which can affect nonlinear interaction in the fiber, self-steepening, harmonic generation, plasma generation, etc., etc. And that is important that this model includes the influence of phase of ultra-short pulses, CAP carrier envelope phase. And because for when we speak about very broadband supercontinuum and the pulses with the duration around one cycle of a cycle duration, for sure it's impossible to omit the influence of CAP on the nonlinear optical processes during nonlinear interaction. And for sure, it's demonstration how we can measure and control CAP in our case. So there are two methods of CAP control, active and passive. And fortunately for physics and for us, optical parametric amplification proposes that Euler pulses has stable CAP. We can control it by two F2 interferometry, and you can see here that in case of a signal pulses, that fluctuation of the phase of the pulses is more random, but in the case of Euler pulses, the phase is more or less stable, around 100 milliradians. And what's important, we checked if the stability, we checked the stability of the phase after it passes through our fiber, and it's a little bit worse than on the entrance of the fiber, but still the stability of the phase is very high. And that is important. We can not only measure, but we can control the phase of our input pulses by changing the delay time between Euler and signal pulses in OPE system. And here we can see the shape of Moscow State, or main building of Moscow State University, in CAP domain. So we can control the phase of the field. And just the results which I showed 1 year ago on also ALT ALT 22 conference. We directly reconstructed the duration of generated pulses, and directly we mean by means of the XCF spider technique. And we showed that the duration of our pulses is around 6 femtosecond, and it is a bit more than 1 cycle. So, but for sure, such short pulses, and it's possible, do not take into account the phase of such pulses. And we tried to observe how it really can pronounce in our experiments. And what we see that during supercontinuum generation, it's possible to observe interference fringes in visible range. So here it's possible to observe a real difference between 2 palm pulses with a difference of C of half of pi. That means that really the system feels the CAP, the dependence on the phase. And why, and what's the reason of this interference? What's the reason of this interference? Just again, the period of such dependencies, pi. And what's the reason of such interference? It's possible to find 2 candidates. The first one is the generation of plasma internal electrogen. The second one is the interference between broadband third harmonic generation, which generated on the last stages of a fiber, and supercontinuum. Numerical simulation shows when we switched off all 2 mechanisms, there is no fringes. If we switch on interference between third harmonic and supercontinuum, we can observe fringes. Here it's only influence of plasma generation, and here it's both mechanisms. So plasma generation does not affect, have very low influence on the interference picture. So it's really generation interference between third harmonic and supercontinuum. And this happens actually in very narrow area of input parameters of the pulses, energy, and input duration of the pulses. And so, for example, is pump pulses around 15 microjoule, and here is the pulses, whereas the most short pulses are generated pump pulse around 19 nanojoule. But when we increase the power, the energy from soliton, just again, the main nonlinear process which is responsible for generation of ultra-short-lived pulses is soliton self-modulation. And in this case, when energy it's too much amount, soliton emit energy in dispersive way. So it's no way to generate shorter pulses. And how to extract information from this interference picture with interference map. So very simple, if just to write spectral interference between soliton and generation of third harmonic generation, it's possible to find out that it depends on the phase difference between soliton and third harmonic and 2f-CAP. So it's just because the period of our interference is pi, because here it's 2f-CAP, that means that period is only half of cosine's period. So after that, it's and we can actually to find from this phase, CAP phase, from this interference map. Then, just following this simple estimation, we can reveal the difference between spectral phase of soliton and third harmonic generation. So here we can directly retrieve spectral phase of our short laser pulses. Here we can retrieve it's in petahertz, so it's in this scale in wavelengths. So here we can say that the spectral phase of third harmonic can be revealed from our maps, and here we just in this 20% of spectral broadening of spectral width of our pulses. So the spectral phase here is flat. That means actually we can retrieve the real pulse duration. If we know the spectral and spectral phase, so we know everything about our pulses. And our estimation, so it's experimental theoretical estimation, say that the duration of our pulses is around 2.5 femtosecond. That means for the central wavelengths of this, for the central wavelengths, that means it's the 1.4 cycle of the pulses. And the peak power of such pulses is around 2.5 gigawatt, and this combination of high energy and very short duration opens way for many applications, and we are planning and doing experiment on generation, as I saw in the beginning introduction, of very short current in semiconductor, and to create on petahertz scale. So I'm finishing. So just again, so we generated and we experimentally prove that the duration of our pulses has 1.4 optical cycles with very high peak intensity. And thank you for attention, and just, if possible, a couple of words. I came here the first time in Samara, and when I walked down on the street, I noticed the library. It's the name of the library, named by Nadezhda Krupskaya. It's the city library. And actually, my first library in Moscow also was named by Nadezhda Krupskaya. And as you remember, many people visited library, stay a lot of time, read books, communicated. So it was around in the evening, around 7 p.m. I came in, and young people were still there. So it was so pleasure to notice that young people read books, not only internet, let's say. So thank you very much for organizers for just again for Kharkov.
Interesting report and good words for Samara. The question, please. So, okay. Next, thank you.
Thank you.
Is it the limits for the communications, or is it maybe useful?
No, for sure it's useful, and I try to emphasize at the end of my talk that we are currently making experiment on generation of impression
Поэтому сам по телевизору будет, да?
optical, or very fast optical device.
Да, да.
Yeah, no, it's possible. It's possible.
So, thank you. Next report, Shorokhov, Moscow State University. Please.
Could you hear me? Hello? Could you hear me? Please give me some feedback so I can proceed with my presentation. Hello. Yeah. Okay, great, great. So thank you for your introduction. Today I will tell you not about the whole story, so I decided to skip the first part, so I will not cover nonlinear light generation today in order to make my presentation more coherent and logical. I will focus mainly on the second part, on the emission control in nanophotonic structures, which combined with 2D materials. And I want to start my presentation with some acknowledgements. This work has been done in collaboration with different teams. So the team from our group in Moscow State University, people from this group mentioned on the slide. Also, the team of Professor Tatiana Shubina and Alexey Torpov from the UF PTI from St. Petersburg. I want to acknowledge their contribution. So they help us with the transferring on the thin films onto our samples and also with some photoluminescence measurements. And also want to acknowledge the participation and help from the Priezzhev University, from the group of Professor Isabel Schauder. They provided us nanophotonic structures, which we used in our experiments. With that, I want to briefly outline my today presentations. First of all, I will give you some brief introduction into mu-resonant nanophotonics and what it can be used for. Then I will focus on integrated nanophotonic devices, so how mu-resonant structures can be used to guide and shape light on a chip. Then I will narrow down on some specific structures, namely hybrid resonant integrated devices coupled with thin films of 2D materials. And then I will provide you results of our work in this field, namely effective light coupling with mere-resonant waveguides composed of silicon nanodiscs. And then I will show you our results of numerical simulations for the 2D heterostructures, which coupled with integrated nanophotonic cavities based on silicon nitride nanoparticles. Okay, let me start with a brief introduction into the topic. Mirrors and nanophotonics is basically connected with small nanoparticles, subwavelength nanoparticles, made of materials with high refractive index and low losses. Such nanoparticles can possess specific excitation, specific modes, named electric modes and magnetic modes. And by tuning the size and shape of these nanoparticles, we can control these modes and provide some peculiar scattering effects. For example, we can suppress backward scattering, increase forward scattering to control to achieve almost 2 pi control over the scattering phase. And this is very important when we consider these nanostructures in combinations. So we can combine these nanoparticles, for example, in the form of metasurfaces. And these structures can be used to control light on demand. Basically, during the last few years, there were a lot of interesting demonstrations from metal lenses up to some specific beam shapers based on near-resonant nanophotonic structures. Nowadays, the structures can be fabricated via standard techniques on CMOS fabric, and so that's why they can be scalable and can be easily introduced in the mass market. But today, I will focus on some other area which is not so fully covered in the media, in the papers. So I will focus today on some integrated nanophotonic devices, which are based on this kind of resonant nanophotonic structures. So please tell me if it's okay and you can hear me and you can see my presentation. Hello?
Да, все в порядке.
Can I proceed? So, yeah, sorry. I just sorry that I saw that my presentation is not shown on the slide. Okay, sorry for the interruption. So today I will focus on the integrated photonic meta devices, which is based on near-resonant nanoparticles. So it has been shown that these structures can control light on a chip, so they can guide it without significant losses through the excitation of the coupled modes in the structures. Also, on a chip, for example, in a slab, we can make some specific structures which we can also call metasurfaces, and these metasurfaces, subalpine structures, can help us to control the light wavefront on the chip, providing opportunities, for example, for focusing. It can be used for some compact adiabatic couplers, for example, for grating couplers, and it has been shown previously. But these structures are mainly limited in functionalities because silicon, as we know, is indirect bandgap material. And for example, if we want to create some active devices on the chip, we need to combine the structures with some specific materials. For example, it can be done in the form of integration with thin films of 2D materials, especially with so-called TMD materials, transition metal decalcogenide. For example, on the left side of the slide, one of the examples provided. So we can see that a thin film, basically monolayer of tungsten diselenide, is placed on top of the silicon nitride waveguide to make kind of single photon source on the chip. And we can see that when we excite this 2D heterostructure, we can generate light not only in the direction, in the opposite direction of illumination, which is shown on the central picture, but we also can couple some of these emitters in this field into the waveguide, into the integrated waveguide, and detect light on the edge of the chip. So only emitters which is placed on top of the nanophotonic waveguide can couple into this waveguide. So nanophotonic structures, resonant nanophotonic structures, were also combined with 2D materials in order to provide some boosting of Purcell effect. Also, they can shape radiation pattern, the scattering diagram in the free space, but they are not so usually used for control light on a chip. So we can highlight different limits or weaknesses of the conventional structures. First of all, I want to say that for silicon waveguides, the radiation mostly located in the core of the structures, so in the core of the waveguide, and only weak leaky modes can feel their environment, and that's why it's really hard to couple radiation from some emitters placed on top of these waveguides. So it's one of the main weaknesses of the conventional silicon waveguides. The second problem which we also faced is the random position of emitters in 2D structures. So we saw it on the previous slide, and really we cannot do a lot of things with this problem. Probably, especially some smart straining design can be used, and it has been demonstrated previously, but I will not cover it in my presentation. And the last one, but not the least, is the random orientation of the dipole moments associated with this localized emitters. So if we will go back on this slide, so these emitters which excited in the thin film of 2D materials can be randomly oriented in the plane of the film, and it means that emitters which can be oriented perpendicular to the waveguide will coincide with the TE mode of the waveguide and will couple to this mode effectively. But for example, emitters which can be oriented along the waveguide almost will nothing give nothing to the radiation which will be coupled to the waveguide. And this is a problem because we cannot control it in the monolayer, for example, in the monolayer of TMD film. Considering these problems, we can state that even for the best case, for example, for the right dipole orientation for the film placed on the conventional strip waveguide, we can achieve only about 10% efficiency of coupling between the radiation from the emitters into the silicon photonic chip. And this a big problem which we want to solve with our design. So first of all, we decided to change material because, as I said, the last problem is that we have some random orientation of the dipole moment associated with this excitonic emitters. We discovered that some materials possess so-called out-of-plane dipoles. For example, indium selenide is well known for their gray excitons, which has the specific nature. So the dipole moment associated with the excitonic emitters are radiant out of plane in the film of this indium selenide film has been demonstrated previously. Indium selenide is also a good choice for our task because it has the photoluminescence in the area close to 970 nanometers, which is close to the transparency window of the silicon, so we can use a standard silicon nanophotonic structures to guide the slide on a chip. And we also decided to change the typical strip waveguide, the conventional strip waveguide, and to put some nanophotonic resonance structures in the center of this waveguide to better couple light emitted by the film itself through some mode matching between magnetic dipole resonances of the disks and these excitonic emitters in the indium selenide field. We started with some numerical simulations. We designed the structure, optimized it for better transparency in the desired region. So we focused on 960 nanometers for TM mode of the strip silicon waveguide, and we changed the height and diameter of these disks in the center of the structure in order to better couple the light. First of all, in order to for better propagation of the light through this waveguide itself. So we can see that with the best case with indium selenide film can provide almost 100% and transparency of these structures, and also excitation of magnetic dipole resonances in the disks can bring about additional enhancement of the coupling between these localized emitters with the film. So we checked different cases. We placed these emitters in different parts of our structures. For example, we placed it in the center, on the edge, and for all cases, we compare it with the standard silicon waveguides, so strip waveguides, and we can see from our numerical results that almost for all cases we have more than an order another magnitude improvement in comparison with the strip waveguide. So we decided to implement this idea experimentally and validate our numerical results. We fabricated the samples using the standard fabrication techniques, namely electron beam lithography, rectifier etching, and then we transfer thin film of indium selenide using exfoliation technique. You can see our samples, some ECM images of our samples on the slide. Basically, it composed by the central part, which is formed by 29 nanoparticles with diameter close to 250, height of 170. And then we have two strip waveguides on both sides of this nanoparticles chain. And then we have two grating couplers on each side to detect some emission which will be coupled into this nanophotonic structure. So probably I will skip Raman research. Our first experiment was conducted for optical characterization of the samples. We set up some experimental setup for characterization. I will not go into details, but we achieved. We provide an opportunity to excite these structures through one side. So we couple light from the free space for the objective lens into one waveguide grating. It goes through the system, and then we collect the outbound signal with the same objective lens, and then filter our signal both in the direct image and in the backfocal plane of our objective. Results which we achieved demonstrated on the right graph, so with the red line. We can see that it's quite close to our numerical modeling, to our numerical predictions, and we can state that this resonance, this peak in transmission can be attributed to the excitation of the magnetic dipole resonances in each individual nanodisks of the structure. So through this coupling excitation of magnetic dipole resonances, it guides the light, and that's what we wanted in our initial design. So we achieved what we really designed for. Then we conducted photoluminescence research. We used cryogenic setup with cryostat, open-looped cryostat at temperatures about 8 kelvins. So we placed our sample into the chamber and excited with a laser at CW laser at 532 nanometers wavelengths. And then we collected backscattered light with a cooled spectrometer. We conducted different experiments in different configurations. So two main examples. The first one, we excite our system through the objective lens, through this free space. We focus on the film on different sides of the sample. So we focus first on the film on the substrate without the structure. And the results achieved with this case are demonstrated on this graph, on the left graph with the gray line. Then we excite our structure right in the center where disk is located and collect the signal in backward propagation through the same objective lens which we used for excitation. This result is demonstrated with a red line on the same graph. And then we used another experimental configuration. So we excite the system. So we use the green light excitation in the center of the structure, right above the disks, and then we collect signal which propagates through the structure and illuminated through the waveguide grating on one edge and collected through the objective lens. So we compare this results for two cases. The first case is presented on this slide, so we can see our experimental sample. Another one was done also for the same, almost the same configuration, but without disks. So we used the standard conventional strip waveguide. And this result is demonstrated on the right slide. So the red line corresponds to the case when we use resonant disks with the indium selenide film, and the gray spectra demonstrated results for the strip waveguide without nanodisks. So what we can state from these results, first of all, if we will compare film on the substrate and film on top of the disks, we achieved almost 30 times enhancement of the luminescence. And the second statement is that if we will compare the resonant waveguide composed of nanophotonic structures and conventional strip waveguide, we achieved almost two times improvement in terms of coupling efficiency of these emitters into the nanophotonic structure on chip. Our second project was connected not with indium selenide film, which possesses this out-of-plane excitonic resonances, but also another structures, namely 2D heterostructures composed of two monolayers of TMD materials. It has been shown that in these heterostructures, it's possible to excite also the so-called interlayer excitons formed by electron and holes located in different layers. So they provided the same type of out of the plane dipole, which can be, as we saw, effectively coupled with our nanophotonic structure. So we decided to switch our research into this heterostructures of monolayers of TMD materials. But we changed our system a little bit. So first of all, we changed the material itself because silicon steel it's a little bit loosey in this region. So this interlayer excitons eliminate, so they have photoluminescence in the region of something close to 900 nanometers or 920 nanometers, depends on the structure. And we decided to change silicon, which is a little bit loose in this region, to silicon nitride. It's some challenge for design because silicon has a refractive index close to 3.5. In this region, silicon nitride close to 2, and it's really difficult to provide this good refractive index contrast between the substrate and the structure. And so we decided to change the geometry of our system. Now we consider nanobricks, and we composed our structures in the way that we have, as in the previous case, we have two strip waveguides on both sides, some nanocavity composed of nanophotonic structures with taper and widths in the center, and also some Bragg gratings on both sides. It allows us to achieve some resonance in the a region of the interlayer exciton emission, and we demonstrated that for this case, for the best case, we can achieve up to 35% coupling efficiency for propagation on one side and almost 70% for both sides, which is 8 times better in comparison with the conventional strip waveguide. Also, we can improve the Purcell factor enhancement. So in the case of our nanophotonic structures, it gives us 12 times improvement in comparison with the strip waveguide. And also we demonstrated that this effect is quite stable. So even if we place emitters on the edge, we still achieve better results. So we outperform the case of the conventional strip waveguide. So let me summarize my talk. First of all, I want to mention that near-resonant non-photonic structures can not only can be used in the passive regime when we guide light through the chip, but we also can use it for effective coupling. We demonstrated that in the case of indium selenide films on top of silicon nanodiscs, we can achieve 40 times improvement of the photoluminescence intensity and also almost 2 times improvement in light coupling between nanodiscs in comparison with conventional strip waveguides. And for designed nanophotonic cavity, we demonstrated up to 8 times improvement of the coupling efficiency and almost 10 times improvement in terms of Purcell effect, Purcell factor. So thank you very much for your attention, and I will be happy to answer your questions.
Thank you. Any question?
afternoon, and welcome back to this second session on this laser diagnostic and spectroscopy. The first talk, LD15, is on diode laser spectroscopy of metastable atoms of heavy inert gases in high frequency discharge plasma by Professor Chamrishaw. Please, Professor Chamrishaw.
Physical Institute, Samara branch. Electrical discharge in gases are used for agriculture soil analysis. Electrical discharge. Electrical discharge motivation. Yes. So, electrical discharges in gases are used from agriculture, soil analysis installation, to space, plasma energies of satellites. In between are medicine, microelectronics, nanotechnology, and fundamental physics. It is convenient to initiate electric discharge in noble gases due to chemical inertias. During a discharge in noble gas, some neutral atoms are excited to long-lived metastable levels. Metastable atoms determine many processes in gas discharge plasmas. Hence, they needed for their diagnostics. Diagnostics can be based on diode laser spectroscopy. The linears of noble gases fall into spectral regions accessible to diode lasers. Our group is aimed at studying the gas discharge active media of optically pumped rare gas lasers, OPRGLs for short. On the left is generalized diagram of levels of inert gases included to lasing cycle, OPRGL. The lasers operated at near atmospheric pressure. Therefore, collisional Browning shift coefficients for optical pump and lasing lines are required to optimizing OPRGL. The table shows the noble gases as well as the lines corresponding to optical pumping and generation. The spectral lines highlighted in blue already have been studied by us. Unstudied spectral lines are marked in red. The gas discharge chamber of our laser is shown below. In the framework of impact approximation, the Browning of WL and shift delta nu of spectral profile dependent linearly on the concentration N or pressure P. Factors zeta and beta are the designed collision coefficients of Browning shift of spectral lines. They are dependent on temperature as T to power 0.3. This parameter can be easily determined from the linear dependence of atomic line Browning shift on concentration N if the gas temperature is constant. In the gas discharge, increase in pressure P causes variation in temperature T, and the collision coefficient change accordingly. Therefore, in a gas discharge, it is necessary to measure differently For each pressure in the sample cell, the gas temperature is determined. When the broadening WL and shift delta nu of atomic lines are reduced to reference temperature, usually 300 Kelvin. Using dependence T power 0.3, finally, the collision coefficients for reference temperature T0 are determined from the linear dependence of reduced broadening shift of line profile on pressure. The values of broadening WVL, shift delta nu, and gas temperature T or Doppler wave WD are conveniently determined from Voigt profile. The correction factor for broadening shift is when the ratio of Doppler width for T and T0 to power 1 divided 4. The technique is limited in pressure, no more than 100 torr. Otherwise, the Doppler broadening from Voigt profile is difficult to determine. The question is whether the measured coefficient can be used at atmospheric pressure, as in OPRGA. Estimate of concentration Nm at which deviation from linear APS can be made using the Weisskopf radius. In our experiment, the critical concentration is 3.4 multiplied 10 to power 20 centimeter minus 3, or 30 atmosphere in pressure. Therefore, our measurements results are also suitable for OPRGA laser. The measuring setup consists of three main parts. Firstly, this is a measuring cell with a radio frequency discharge excitation units and gas pumping system. Let's consider the advantages of radio frequency discharge. There is no high voltage here. External electrodes do not pollute gases in the discharge. The radio frequency discharge operates with a low electron concentration. Therefore, the stark broadening shift of spectral lines can be neglected. However, good shielding is needed. The second element is a low pressure reference cell with an exciting radio frequency generator. When studying argon and neon, inconvenient to use starters from fluorescence lamp. The third element is tunable diode laser with a set of spectral diagnostic equipment. Commercially available and laboratory-made diode lasers with external resonance were used. Inset show the type of recorded signal. The blue signal is received from measuring cell. The red signal is registered in reference cell. For each pressure in measuring cell, shift and half width of blue signal were measured. Let's discuss what source of error exists here. The power of probing beam should be 1 to milliwatts. Otherwise, the atom's transition becomes saturated and additional line broadening occurs. Radial and longitudinal temperature gradients arising in discharge region can distort the value of collision coefficients. The radial temperature gradient occurs due to heat transfer to cell walls. It has parabolic profile. This gradient can be ignored if laser beam is directed through the center of discharge using a pair of attitudes. The longitudinal gradient arising due to heat transfer to walls and convectively heat removed by the gas flow. Similar gradients have been studied and applied to fast flow CO2 laser. It has been established the shape of longitudinal gradient depends on parameter A. Determined by expression given at the top of a figure. Under our conditions, the values of A will be in range of 0.3, 0.75. This means that temperature increase abruptly at the upstream discharge boundary. The gas is quickly heated to maximum temperature, which does not change until the lowest point of discharge, when the gas is rapidly cooled to ambient temperature. Modeling has shown that with a similar form of longitudinal gradient, the systematic error in value of condition coefficients does not exceed the permissible 3%. The figure shows the dependence of reduced width WVL and shift WVC of 912.3 nanometer argon line on the partial pressure of disturbing gases. The dots represented the measurements, and the soil lines represents the feed. Linear of measured linearity. The linearity of measured dependence is confirmed by the coefficients on determination R power 2 closer to unity. Helium causes the greatest line broadening, and neon the least. Argon and neon shift the line to the red side, negative slope. Helium shifts the line to blue side of spectrum, positive slope. The red shift for argon and neon indicate a predominant attraction between the emitting and perturbing atoms. The blue shift of spectral lines corresponding to the dominance of repulsion between argon and helium atoms. Similar dependence were obtained for the argon line 811.5 nanometer. Neutral neon is mixed of three isotopes. Relative content of isotope in mixture is shown in the figure. The atomic transition lines corresponding to different isotopes are shifted in spectrum. Therefore, in natural neon, especially at low pressure, the profile of 703.2 nanometer line appears to be an envelope of two close lines. During processing, the fitting of a recorded spectral contour must be performed using a corresponding composition model profile. Our model profile represented the sum of two Voigt contours. The model took into account the isotopic shift of lines 1.6 GHz, difference in amplitude and values of Doppler broadening of 20 and 22 isotopes. The contribution from 21 isotopes was discharged due to its smallest. The figure shows an example of approximation at low and high pressure. The residual difference between measurements and our model is on average less than 5%. Thus, the parameters of spectral lines of isotope 20 can be determined in natural neon. The figure shows graphs of reduced broadening shift of 603 nanometer neon line, depending on partial pressure of disturbing gases. Linear dependence is confirmed by the values of the coefficients of determination close to unity. In helium, shift on considered lines was at sensitivity limit of our technique. In pure neon, linear shift is larger and directed towards the red side of spectrum. The measured values of slowed coefficients are shown in the figure. Similar dependence were obtained for neon lines 640 nanometer. Krypton line. Natural krypton consists of mixture 6 stable isotopes. A simple model profile formed 4 lines of even isotopes does not work. The reason is influence of the hyperfine splitting components of line of ordered 83 isotopes. Our model profile was formed as the sum of 19 weighted and shifted components of Voigt profile. Additionally, the model took into account difference in amplitude and Doppler width. The contribution of isotope 78 was not considered due to its insignificant content. Example of approximation of recorded line contour by model profile and simple Voigt profile is shown in figure. Results. Here we presented values of considerable broadening shift coefficient for study argon, krypton and neon lines. All values are given in Hertz centimeter power 3. Helium causes the greatest line broadening and relative weak blue shift. The remaining inert gas shift the lines to red side and argon shift it mostly strongly. The random error precision of obtained results within 5–10%, which sufficient for modeling OPRGL laser. Systematic error or accuracy of results is difficult to determine from incomplete literal data. A method to measure collision broadening shift coefficients of spectral lengths of inert gases in radio frequency discharge is proposed, that does not require thermal stabilization. The broadening shift coefficient for 5 CP transition of argon, krypton, and neon atoms were measured. The measurement precision was 10%. The studied transition relative to the generation cycle of optical pump rare gas laser. Conclusion: calculation based on Lincoln-Foley theory and van der Waals potential are consistent with the result of measurement of a rare gas mixture or of not containing helium. The accuracy of measurement collision coefficients is estimated at 25%. Thank you for your attention.
You covered the spectral region in between 7 and 900 of nanometers. 700 to 900 nanometers. Different transitions. Do you use different lasers for that?
Yes, we use it.
But what kind of laser do you use?
Микрофон.
We use semiconductor.
What type of lasers do you use? And you have different wavelengths. Are there 3 lasers or 1 laser?
3 lasers.
3 lasers. What type of the lasers do you use?
First lasers with external cavity lasers from theta wave.
This is commercial.
Yes,
Is it quantum cascade or is it conventional injection laser?
this is quantum wave.
At what is the tuning range?
26 nanometers.
How you calibrated it? Frequency calibrated.
We use it Fabry Perot.
Yeah. What
Constant
length? Quartz? 10.
spectral range 1.5 gigahertz.
And what are the densities of the metastables?
Roughly 10 to the power
It is precious.
13. 10-13.
Would you please go to slide 8?
He has removed his chain.
Okay.
Hey.
Yes, yeah. Could you please explain me again that so your peak here is not symmetric, so you have like 2 peaks. So one, what does do the peaks correspond, and when you increase the pressure, how the first peak is not so clear, like at low pressure. Thank you.
Okay. 2 peaks between natural neon contain 3 isotopes. You see?
Yes.
20, 22, 21. This peak corresponding 22 neons. This peak corresponding 20, 22 isotopes. When the pressure increases, broadening line, yes?
Yes.
Not clear here.
Okay, and then we will see the isotope 21. So because of low concentration, as I suppose.
Чего он спрашивает?
За низкой концентрацией.
Так мы не видим 21.
Є. Zero point 97%. Вклад этого изотопа пренебрежительно.
Thank you.
Any other question?
Вы пробовали определять температуру газа в активной среде по уширению?
Я плохо рассказал, но именно так мы и
Прошу
работаем.
прощения, какие значения температуры?
Ну, зависит от смеси. Обычно от 300 до 500 кило. 300, 500 кило.
Я тоже, возможно, пропустил. Вы рассматривали переход только с метастабильных уровней или резонансных тоже?
Нет, постановка какая? Laser cycle. И он имеет две важные линии. Накачки, optical pumping и laser generation. Для них и нужно было.
Причем?
Нет, а у вас там было написано 5 уровней СП мультиплета.
5 линий.
5 линий, хорошо.
Yes. Probably the question is about that we have heavily populated two types of levels, metastable and the resonance levels. The first one is simply because of the transition to the ground state is forbidden by spin or by another, but resonance levels, they are populated because of trapping of radiation. It's not metastable, but resonant levels. The question is about this. What is this? What level is resonant and what level is
This is resonance level.
metastable?
This is metastable level. And we studied two lines. This line, optical pump line, and this line, generation.
Emission. What level is metastable and what level is resonant?
1C5 metastable, 1C4 resonance level.
Okay. With this, let us thank the speaker and give him a next invited talk in this session is on fast sensitive laser absorption spectroscopy by Dr. Professor V. Oshikin. Please, Professor.
Включите, пожалуйста. Good day, colleagues. I will tell about the absorption spectroscopy. This is a very old technique, very old spectroscopic technique. I think that everybody knows what does it mean. This technique elder than each of us, even me. So, what's the question in such situation? The question is, I have to discuss the possibilities of existence, not technical, but basic limits for this technique, this traditional absorption technique. And I will mainly discuss the problem of the time resolution of this technique. What's the question? The light указатель. И, да? О, что-то не то. the light pass through the medium and have losses in intensity, and these losses can be related to the density of absorbed particles, what previous reporter demonstrated. Yes, but what is really happens? Let's consider the rarefied media like gas or plasma, something like that, and we'll consider the isolated spectral absorption linear. I do not see a pointer. Where is it?
Нету, Владимир Николаевич.
Нету его, да?
Что там, должно быть видео?
No point. Yeah. Anyway, you can see the separated absorption line with this profile, and to get this with the half-width delta nu, and you are interested to get the profile of this spectral line. To do this, you may tune the frequency of your lights. Где pointer? Oh.
Он, наверное, яркий экран, он не пробивает его лет.
Вот я и смотрю, что-то не получается. Спасибо. Ладно. Значит, first, I have to tune the frequency across this profile, and to get the profile correctly, you need that the width of the probing light has to be smaller than the width of the spectral study. This is evident. And the next question is, if you are interested to get this data with time resolution, then you will get really problems. Why is it so? We can refer to the, for example, for simplicity, we can refer to the uncertainty relation, this one, from which it follows immediately, then you need to spend a time to record this profile more than the reversal width of the line. This is simply a consequence of the uncertainty relation. This is estimate, but what does it mean physically? It means that during the record, all processes include kinetic motion, relaxation of the quantum states, exchange of energy, and losses of energy, and so on, has to be overed. You have the stationary spectra. But at modern technique and modern problems, you need a more fast registration. What will be happening? Evidently, if we will not have the stationary spectra, then we will get the transients. This is for every oscillator exists. And the question is it possible to use such transient spectra for quantitative measurements as it normally practiced? And this question has the story. At the first time, it was studied by Bloch in 1946. He investigated the paramagnetic properties of nucleus and the transition in between the magnetic sublevels. And he specifically he stated that these transitions have to be non-stationary, even at slow spectroscopy, slow rate spectroscopy. 2 years later, in radio frequency range, in the group with Parcel, this theory of Bloch was confirmed. And these works were so sound, and what is more important, they are strongly promoted the invention of the nuclear magnetic resonance as a diagnostic tool, especially in different areas, especially in medicine and so on. So in a couple of years later, the Nobel Prize was condemned to Bloch and Parcel. This is very bright works. Since that and later, a lot of works have been performed in this area. And the mainstream was to extend the studies of the transients for different spectral ranges, from energy, photon energies from milli-electron volts radio frequency up to hundreds of kilo-electron volts for Mössbauer lines in nuclear physics. As was it interesting, the most problematic was the invasion to the optical region. And the problem was that to get the transients in optical region, you have to realize the frequency tuning range up to at least 10 to the 4th wave number per second. At least. And compare one wave number in radio frequency and also one wave number in nuclear physics, because the Mössbauer lines are very narrow. But optical region is complicated with these circumstances. This problem was shifted when the fast tunable lasers became available for this region. And first of all, this is the diode lasers. And the first work was published in our group in 1988 for infrared region. That was the work of Savitsky et al. From our group. And it was quite a unique result, and it was not reproduced in 15 years approximately. Only after the quantum cascade lasers became available, it became possible to observe such kind of transitions. This is since 2003 and later. This is an example what I mean as a transients. This is the first our work. This is the profile of CO2 molecule absorption line at the tuning rate about 2 megahertz per nanosecond. You see more or less normal profile, more or less. But if you use the rates 10 times faster, then you see the oscillations of this signal. The regions exist with absorption, the regions exist with superluminescence, the oscillations, the damping of oscillations, and a lot of specific features. That is quite similar with those then in 50s, in late 40s, was observed by Parcel. This typical transient, this was with conventional jet laser, and this is a French group, maybe 20 years later about this, with much faster quantum cascade lasers and more detailed resolution. They studied the rate of relaxation processes with this picture, because such experimental results can be discussed with the help of the quantum theories. This may be the theory of Bloch with his vector modality, theory on the basis of the matrix density equation and so on. So the theories exist. And the comparison results with the theory shows that the results are sensitive to the type of elementary process and the intermolecular structure and external conditions and so on. And it was the field of studies of elementary processes, of the structure of molecules and so on, and the Moster group concentrated on these questions. This field became very crowded, and that time we left it because too much people were involved in this. It was not interesting. But a couple of years ago, when I simply, for myself, interested in the progress in this field, I mentioned that the very important question is still in shadow. What I mean? I mean that this fast spectroscopy is not able to execute its main destination, the measurement of the densities of the particles. And what is the reason? What is the reason for that? We think that all spectroscopy, all quantitative spectroscopy, is based on two main relations. This is the old relations, Baer-Bouguerie-Lambert, which is for the losses of the correlation in between the absorption coefficient and velocities of intensities, and the correlation in between the integral absorption with the difference of the densities of the optical transition states. Yes, but, and everybody uses it. It works, but it is by silence agreement, it is undermined that during the measurements, the structure of the absorption coefficients became the same. It conserves. But we have seen that in our case of fast spectroscopy, it's not so. It changed. So one can conclude that the absorption spectroscopy fails in this situation. And the question is, can we save this situation? And we provided the following. Let us take a step back from quantum theories. And we'll try to discuss the classic analog of this effect. To our view, what happens, really? If this solid curve is the real line profile, this is, say, the absorption coefficient, for example, and the frequency moves right to the left. What happens when the frequency of the line the light with this frequency begin interact with matter? It absorbs, but if absorbs, it polarizes. If polarizes, that it's emit. So the probing light stimulated the own emission of the medium. Being coherent, these two beams follow each other and make the interference in between. So in the plane of the detection, something there, you have the interference picture. And we get the signal not only the real absorption, but it's superimposed with this interference picture. And if we will find a way how to purify this normal signal, then we can probably use these classical absorption relations. And what's possible? If the frequency moves in this direction, in the very beginning of the interaction, the absorption is small. In this place, this is large, so the induced emission is strong. At this point, the strong induced emission is weak. So it means that when moving in this region, the region of this wing of the profile, we are free of these artifacts. And if we will concentrate our attention on the profile of this wing, then probably we can able to restore, to reconstruct the whole right profile, static profile. But to do this, we need a reliable model of the profile, because to restore the whole from the part, you need the model of the whole. This is always. There's a lot of details I will not explain. And we took usual Voigt profile. This is normal definition. S is the line strength, P is pressure, delta nu L, delta nu D is the Lorentz at Broughton, and the Doppler width. And the delta without indices, this is the Lindholm central shift. And what is important in this situation? If we consider two mechanisms of broadening, Doppler broadening and Lorentz broadening, then it means that Doppler broadening works without the phase shift. But the Lorentz mechanism is based on the collisions with break-off phases. If we look for the interference picture, that it means that we see the coherent processes of the input light and the self-emission of the media. And it's important, does it coherent exist or it will be destroyed in these conditions or in these conditions? And for this, we have to take into account not only collisions, as usually people undermine, but also in other processes. And when analyzing, we conclude that for our conditions of the low pressure, and we are talking about sensitive measurements, where the density of particles is small. The important also, no, this is normal Lorentz collisions. This is saturation. And the phase breaks because of Rabi oscillations. It also kills the coherence. Also important became the limited time of flight, the particles across the laser beam of pumping line. This also killed the coherence. And finally, also decay effect take some input in this process, because this is a Doppler narrowing, but it becomes with the breaking of the phase, because the free path of excited particle is less than the wavelengths. It so means that the phase breaks. So all these mechanisms we have to include in these terms, in Lorentz term, here and there. All these mechanisms. And also we have to take in mind that when at first tuning, the instrumental function width depends not only on the detecting scheme, this is pure instrumental function, but also as an uncertainty of the frequency because of fast rate. You have to take into account this. So this is what we have to take into account following our simple interference-based model. How it works in reality. This is three pictures. This is absorption lines of acetylene, and for sunline, that's not necessary, not so important. The markers is the experiment. You see the traditional absorption, superluminescence, and so on. And this is a pure gas at low pressure, approximately half a torr. This picture is for the same amount of acetylene, but with addition of 20 torr of nitrogen as a buffer gas. C is also the same amount of acetylene and 100 torrs. And we see that the profiles are essentially different. What we are doing in accordance with our proposal. First, we took, and the frequency also moves from right to left. And the rate of tuning is 200 megahertz per nanosecond. This is a very high frequency. It's about 10 to the 6 wave numbers per second. These quantum cascade laser experiments with fast tuning. If we find the best fit of this right wing, then knowing the instrumental function, we can find the convolution of the real profile with the instrumental function. Then at the first step, if we rectify our result, our fitting results from the instrumental function, that we give the real profile. And in principle, we can work with this real profile to obtain the densities. You see that the same scheme used in all cases. You see that the real profile, which is number 1, number 2, this is the convolution of the real profile with instrumental function, the markers is the experiment, in all cases. Okay. You see that at this case, the real profile have nothing in common with reality, nothing in common. You see in the case C, the real profile is quite close to the real, and this one is something intermediate. So situation may be very different. So let's try to measure the concentrations from this data. This is measurements of the concentrations. This is again the same cases. This is a pure gas at low pressure. This is added 20 torrs of buffer gas. This is 100 added buffer gas. And the dashed line, horizontal line, this is a real density of particles. What we can do? We can apply the classical relations for absorption just to experimental data. And you can see that you get the difference between the reality and measured approximately 2 times. This is an example, maybe more, maybe less. In this case, 2 times difference. Then we can do another approximation. We can approximate the experimental spectrum as a whole by Voigt profile as a whole. Then we get these triangle results. It's not much better than direct approximation. But if we use our scheme and we reconstruct the real profile from the wings, then we get correct results in all diapason of pressures of buffer gas. It's not surprising that all 3 schemes at high pressures works well, all schemes, because the collisions are strong and they kill the coherence almost completely. But in this case, the main mechanism, let me see. No. In this case, the main mechanism to destroy the coherence is the time of flight effect. Not collisions, but time of flight effect. The saturation is negligible, the collisions are negligible, the time of flight effects works. In this case, both mechanism works and the collision relaxation becomes. In this case, the collisions defeat all other mechanisms. And everything is okay. So because of time, I had a summary. First, we are talking that the non-stationary effects prevent the possibility of measurements of direct measurements of the particles. The second is what we have to do to avoid it. I explained it. Because we see not the real spectrum during fast tuning, but we see some kind of phantom of the spectrum. And if we use our proposal, then we can rectify the real signal and the artifacts. We can purify that. And we demonstrated ultra-fast sensitive concentration measurements. What I mean ultra-fast? In this example, what I show, you can measure the density of particles at very low level at 1 nanosecond. I don't know other schemes which make it possible. So this is the main conclusions. Thank you.
Does this effect depend on intensity of formulation? Because we are talking mainly about the growth. This is a small intensity, but it doesn't mean that the saturation does not exist. Because you see in your profile both the regions with the absorption and the region with the superimposition, so it creates the inversion. So some part of profile, even at this low intensities, in the range of 10 millivolts. But nonlinear effects, so it depends. And at the same intensity, but tuning across the profile, the intensity practically doesn't change because the absorption is small and the intensity of the is approximately the same. All interference, all distortions became due to the induced emission of the medium. So this is combination of the heat and No, I mean, even or a small intensity, one kind of experiment, and next experiment, a higher intensity. What's happening?
I do not have it with me, this picture, but it depends. But the range of the available direct lasers include the conformal lasers, conventional injection lasers. It is not very high intensity. This is the level of milliwatt, 10 milliwatt. This is the range. And people even surprised when I discussed it in my seminar. At few milliwatts you have the saturation. It's not possible. It's possible. Because the density of particles is small. If you observe the picture, I will show you formula which demonstrates. Предыдущий, да. Можно вернуть? Или вы уже сошли? Вот я здесь, кстати, да, вот отвечаю на ваш вопрос. Эффект насыщения. Вот, который я сказал, что из-за раби эффекта, вот эффект насыщения приводит к сбою фаз, разрушает когерентность. Вот это сигнал параметр насыщения. Он зависит от частоты раби, а та в свою очередь зависит от квадрата обратного давления. Мы обычно всегда говорим о параметре насыщения, когда говорим о лазерах, которые работают там при сотне стор при атмосфере и так далее, и так далее. Здесь мы говорим о чувствительных измерениях. Когда этих частиц мало, их давление малы, насыщение возникает. Но оно, в общем-то, вот я говорил, что где-то проявляется, где-то не проявляется, в принципе, не может. Но вот вы говорите, что можно там при такой интенсивности, при такой интенсивности проверить. Таких данных нет. Дело в том, что все лазеры диодные, и классические, и квантовые каскады, они так сделаны, что более-менее интенсивность у них должна выдерживаться для того, чтобы не пройти. Поэтому какой-то лазер работает на личность. The question was in Russian and I became transferred.
Why you can't use the whole data of your measurement? Because if you clearly understand the coherent processes in your system, you can calculate it and reconstruct the concentration. And in this case, you will use the full bits of your experimental spectrum, but not only the wing.
We do not see the whole profile. What is the stopping?
If you go forward,
See, when frequency comes from here to there, that in the beginning of interaction, the media is not polarized, right?
yes, I understand this. Go to experimental data.
This is a model.
But
This is a model. We use this model. How to
yes.
how to
In this case, you can calculate the full
the
spectrum.
real.
Okay, maybe.
It's not experiment. This is a.
Maybe you can
This
discuss.
is
I
proposed
also have some.
scheme of processing.
I also have some question. So let us thank Professor for the very nice information. And I invite my co-chair, Professor Evi Fedotov, for the next, for chairing the session for the next part of the oral.
Okay, let's thank Professor Khan for chairing our session. And my name is Andrei Fedotov, and just we already out of schedule, so let's keep ourselves in the frame of the schedule to have enough time for lunch, okay? The next talk will be given by Dr. Yuriev.
Doctor.
Okay, future doctor Yuriev from Russian Federal Nuclear Center from Sarov.
I'm apologizing, but I prepared my speech in Russian. Will you allow to tell me in Russian?
What? Do you want to speak Russian? Yes. So, if our guest
No objections.
is no objections, so we.
Is it possible?
So,
Yes.
I'm apologizing.
I'll read that.
So probably it's a good chance to learn Russian for you.
Thank you very much. Итак, меня зовут Юрьев Алексей Валентинович, я молодой специалист в Институте лазерно-физических исследований в ядерном центре в городе Саров. И я представляю свой доклад на тему определения концентрации метастабильных атомов аргона в активной среде лазера на метастабильных атомах аргона. Так. Прежде чем переходить к целям и задачам, хотел в двух словах рассказать про наш лазер. Это газовый лазер нового типа, основными преимуществами которого являются высокая удельная мощность. Теоретически предполагается съем до 500 Вт с кубического сантиметра активной среды. Высокий квантовый КПД, высокий коэффициент преобразования свет-свет, однородная химическая инертная активная среда. Применяется этот лазер для преобразования мощного излучения диодных лазеров с низким качеством пучка в мощное излучение газового лазера с высоким качеством пучка. На данный момент в нашей лаборатории достигнута максимальная мощность 4,1 Вт. В качестве активной среды использовалась смесь аргон-гелия в процентном соотношении 2% аргона и 98% гелия. На слайде представлены энергетические уровни атома аргона, которые используются в лазерном цикле. Нижний лазерный уровень 1s5 заполняется при прохождении разряда, после чего происходит накачка на длине волны 611 нанометров на уровень накачки 2p9, с которого происходит беззалучательная релаксация на верхний лазерный уровень 2p10, и при наличии инверсии населенности происходит генерация. Гелий в активную среду добавляется для того, чтобы ускорить процессы бесстолкновительной релаксации. Для возбуждения метастабильных атомов используется импульсный периодический разряд. В нашем случае длительность импульса 40 наносекунд по полувысоте с частотой повторения 80 кГц. На слайде представлены фотографии межэлектродного промежутка при прохождении разряда и результаты измерений напряжения и силы тока на электродах. Амплитуда напряжения составляет 1800 вольт, амплитуда силы тока 6 ампер. Конкретно в данной работе основной целью было определять концентрацию метастабильных атомов в активной среде при различных условиях постановки эксперимента, ну и как экспериментально, так и с помощью модели аргона-гелиевой плазмы. С помощью определения концентрации были выполнены два небольших исследования. Именно было проведено исследование по вопросу, какой материал лучше всего использовать для электродов, пока нет какого-то единого мнения. И второе исследование была определена оптимальная доля аргона в смеси. На данный момент мы используем смеси 2% и 3%. Это было проверено в эксперименте и с помощью модели, и также проведено сравнение расчетных и экспериментальных результатов. В двух словах про модель. Кинетика модели насчитывает 24 частицы, из них 18 частиц — это энергетические состояния атома аргона, в них включены аргон в основном состоянии, оксимер, молекулярные и атомарные ионы и 14 нижних уровней энергии S и P мультиплетов. Для аргона включены для гелия включены гелий в основном состоянии, общий ион гелия аргоновый, оксимер гелия, нижний энергетический уровень атома гелия и также молекулярный атомарный ион. Взаимодействие этих частиц учитывается с помощью 476 реакций. Для определения функции распределения электронов по энергиям в модели решается уравнение Больцмана. Для расчета концентрации частиц плазмы в различных точках межэлектродного промежутка используются уравнения дрифта и диффузии. Граничные условия учитывают тепловое движение и вторичную эмиссию электронов. И можно переходить к первому исследованию. Первое исследование было направлено на то, чтобы выяснить, какой материал лучше всего подойдет в нашей установке в качестве электродов. И в первую очередь были проведены вычисления. Ключевым параметром металла является работа выхода электрона из материала электрода. Поэтому были проведены вычисления на примере двух металлов. Это тантал и гексапарит гадолиния. Эти материалы были выбраны, потому что они могут быть применены в качестве электродов, они доступны и они имеют почти в 2 раза отличающуюся работу выхода. На слайде представлены результаты вычисления средней энергии электронов в межэлектродном промежутке для этих двух материалов. Заметно на левом краю, что электроны, получающиеся при использовании гексапарита гадолиния с меньшей работой выхода, после вылета из металла имеют значительно большую энергию по сравнению с танталом. Однако уже на расстоянии примерно 0,1 мм от катода для обоих этих электродов энергия падает до некоторого минимального значения, и дальше энергия остается постоянно одинаковой для обоих металлов. То есть в большей части межэлектродного промежутка какой-то видимой разницы между танталом электродом и электродом из гадолиния наблюдаться не должно. Аналогичные расчеты для этих же металлов были проведены для концентрации метастабильных атомов аргона на нижнем лазерном уровне. Результат представлен на слайде, и как видно из результатов, также нет никакой видимой разницы между этими двумя металлами. Таким образом, при выборе металла мы не должны ориентироваться на значение работы выхода электрона из металла. Объясняется это достаточно, как мне кажется, просто. При вылете из катода электрон попадает в область слабого поля, которая не способна скомпенсировать многочисленные потери, возникающие при столкновении электрона с окружающими его атомами. Плазма атмосферная, поэтому столкновений происходит очень много. И данное предположение было решено проверить в эксперименте, и был поставлен эксперимент, направленный на получение лазерной генерации на вольфрамовых и танталовых катодах во всех возможных комбинациях. К сожалению, гадолиний нам недоступен, только вольфрам и тантал. У них работа-выход, такой экспериментальный результат. Были проведены эксперименты по лазерно-диодной спектроскопии. Это не я. При которых излучение зондирующего лазера пропускалось через активную среду при включенном разряде и фиксировалось на фотоприемнике. Поскольку величина поглощения напрямую зависит от концентрации метастабильных атомов, то по величине поглощения можно судить об их количестве. Зондирующий лазер и фотодетектор были помещены на общую платформу, которая могла перемещаться таким образом, что лазер и фотодетектор оставались неподвижными друг от друга, но меняли положение относительно межэлектродного промежутка. Таким образом, мы могли производить измерения в различных точках межэлектродного промежутка. И покажу ключевые результаты. Ключевое измерение было произведено на вольфрамовом электродах и вольфрам-танталовых электродах, где танталом был анод. На левом графике представлены результаты измерения, результаты зондирования в центре. Как демонстрирует график, нет, опять же, никакой видимой разницы для двух различных электродов. И при использовании вольфрамовых электродов, и при использовании вольфрам-танталовых электродов получается одинаковое поглощение, следовательно, одинаковая концентрация метастабильных атомов. При зондировании возле анода в околоанодном промежутке заметно, что концентрация метастабильных атомов вблизи танталового электрода получается при прохождении разряда такое же поглощение, но затем более быстро тушится. То есть вблизи танталового электрода уменьшилось время жизни. Единственное логичное предположение, к которому мы пришли, заключается в том, что тантал является геттером, и при отключенном разряде он способен в себя впитать, способен поглощать различные примеси, такие, например, как кислород, а при прохождении разряда тантал нагревается, и молекулы атома кислорода отдает обратно в активную среду, тем самым вызывая тушение метастабильных атомов и прочее. В наших ранних работах уже было показано, что для того, чтобы потушить половину метастабильных атомов аргона, достаточно всего лишь 0,02% кислорода в активной среде. То есть даже небольшой танталовый электрод способен вызвать видимое изменение концентрации метастабильных атомов. С грузом данных знаний мы провели эксперимент по получению генерации лазерной еще раз, уже в абсолютно другой подстановке. Мы использовали вольфрам-танталовые электроды и поменяли в какой-то момент полярность. Результаты представлены в таблице. Эксперимент был направлен на получение максимальной мощности генерации, и максимальная мощность генерации была получена при использовании вольфрама в качестве катода. Если использовать тантал в качестве катода, то все-таки генерация, какие-то примеси там, скорее всего, еще остаются, и мощность генерации уменьшается. Таким образом, наша лаборатория пришла к выводу, что наилучшим материалом, который можно использовать в качестве электрода, является вольфрам, поскольку он не поглощает, по крайней мере, не так сильно поглощает примеси и устойчив к разряду. И второе исследование было направлено на определение... Ускоряется, да? Хорошо. Второе исследование было направлено на определение оптимальной доли аргона в смеси. Раз ускоряться, то были проведены, опять же, эксперименты по зондированию. Эксперименты продемонстрировали, что наибольшее поглощение получается при использовании 2% аргона в смеси. Аналогичный для условий постановки эксперимента был с помощью модели проведен расчет. Расчет продемонстрировал, что оптимальная доля аргона составляет при 300 Кельвин 2,3% и 2,7% при 450 Кельвин. Также мы использовали 3 смеси 1%, 2% и 3%. На них также была получена лазерная генерация. При проведении эксперимента мы варьировали значение расхода газа в газовой системе. И заметно, что при небольшом расходе оптимальное значение аргона находится где-то в районе 3%, но при увеличении расхода оптимальная доля аргона смещается к 2%. Поэтому оптимальная доля аргона в смеси находится где-то от 2 до 3% и уменьшается при увеличении расхода. В модели на данный момент не учитывается движение газа, поэтому я воспринимал увеличение расхода по его ключевому изменению в плазме – это уменьшение температуры газа. И на данном слайде представлен расчет инверсии населенности для 3 температур 300 Кельвин, 380, 450. Для 300 Кельвин оптимальная доля 2%, 380 – 2,4%, 450 – 2,7%. То есть модель демонстрирует значения, которые сходятся с экспериментом не только по, собственно, по самим значениям, но еще и по поведению. При увеличении расхода, то есть при уменьшении температуры газа в активной среде, оптимальная доля аргона смещается в сторону меньших значений. Собственно, все я уже сказал. Благодарю за внимание.
Что такое инверсия в относительных единиц?
Я вычислял различную инверсию и делил ее на максимальное значение инверсии, которое получалось при этих расчетах.
Абсолютное значение какое? Абсолютное значение какое?
Относительные единицы.
Инверсия в относительных единицах.
Вы про вот этот слайд?
Да.
Есть.
Значит, вы взяли одну абсолютную величину, поделили на другую абсолютную величину. Что это за величина?
Инверсия, при которой максимальная инверсия.
Что такое инверсия 0,99?
Нет, инверсия единицы просто на графике.
Что такое инверсия единицы?
Я вычислял инверсию населенности для различных доль аргона в смеси. Получал различные значения инверсии в сантиметрах минус треть. И потом каждый из них делил на максимальное значение инверсии.
Это всегда разница в каких-то концентрациях в одном кубическом сантиметре. Что такое единица или там половинка, это
Значение нормировано на максимальное значение.
Я спрашиваю, а какие это максимальные?
В смысле, вам цифра нужна конкретно?
Да.
Это сильно зависит от конкретного расчета.
О каких порядках хотя бы величин мы говорим?
10,
что такое 10 десятых, 10 15,
10 12,
10 19? Ну где-нибудь есть у вас эти данные?
Здесь нет, но они здесь не имеют никакого значения.
Они имеют...
У меня, может быть, там короткий...
Единственное, что имеет значение.
Короткий вопрос такой методологический. Вы в чем мотивация, еще раз, вообще таких лазеров? Потому что, собственно, твердотельные лазеры проводят энергию, там киловатт, а у вас вот с трудом 4 ватта вы получаете.
Далее этот лазер можно масштабировать. Вполне к этому.
Насколько? Тут 2 порядка надо масштабировать.
Здесь КПД до 90%.
Да, здесь высокий КПД, воздушное охлаждение.
Активной среды.
Кстати,
Back to the future, по-моему,
что сейчас достигнуто у вас? Потому что в Штатах там достигнуты киловатты.
На этом лазере киловатты не были достигнуты.
Там на других, со щелочными атомами там, и так далее. Тем не менее, с оптической накачкой достигаются мощности до киловаттного уровня. Вот что у вас?
Получим мы киловатт или нет, зависит, к сожалению, от нас, от финансирования. На этом лазере можно получить киловатт, если им заниматься.
Спасибо. Ладно, давайте поблагодарим. Пожелаем ему найти финансирование, чтобы повысить мощность. The next talk will be presented by our host, Dr. Priezzhev.
Будущий доктор.
Again future doctor. You have 15 minutes.
So, hello everyone. I'm a PhD student at the Samara University, an engineering department, and today I'm going to tell you about flexible infrared detector. So, infrared detectors, especially flexible infrared detectors, can be used in wearable electronics, in e-textile, in health monitoring, gas composition, and air and space crafts. So, the main issues of the existing photodetector sensitive elements are as follows. It is rigidity, they cannot be compressed or bended, also limited spectral sensitivity, low response and recovery times, as well as low detectivity. So in order to overcome these issues, scientists are trying to investigate new materials. And one of the most prospective family of materials nowadays is transition metal chalcogenides. And we decided to use TIS2. It is transition metal chalcogenide, which possesses an octahedral orientation of atoms, and also it is n-type semiconductor with a narrow band gap, which varies from 0.2 up to 0.9 electron volts, which shows that this material properties are depending on its structural quality and number of layers. So the aim of this work is to develop a flexible infrared photodetector based on TIS2. So the synthesis process of TIS2 as follows. We used a vapor transportation technique to synthesize TIS2 samples. So what we did, we took 1 part of titanium powder and 2 parts of sulfur powder and mixed that using mortar and pestle. After that, we sealed these materials in quartz ampule and under vacuum, which was of 2 multiplied on 10 in the power of minus 5 millibar. After that, we heated this solution up to 650 degrees Celsius for 24 hours. After that, we took out our ampule and cooled it naturally up to room temperature. After that, the neck of this ampule was cut off with diamond cutter, and the material was collected. So on the right side of the slide, you can see synthesized TIS2 nanosheets. As we can see, the shapes of our nanosheets are of regular rectangular, and it was the shape which we're supposed to get after synthesis. So now let's talk about functionalization of our nanomaterial. So we took 25 mg of titanium disulfide and mixed it with 1 mg of silver nitrate in IPA solution of 50 ml. After that, we made a treatment with ultrasound for 1 hour. And after that, we drop casted our material on silicon substrates in order to perform future characterization. Like here on left side, you can see some image of our functionalized material. It is TIS2 with silver nitrate, and in the blue circle, you can see 1 part of silver nitrate. So we can see that our silver nitrate attached in bulk to titanium disulfide nanosheets. And on the right side, we can see Raman spectra of TIS2 nanosheets in pure and functionalized form. In case of pure form, we can see 2 significant peaks, which are EG and A1G. EG, it is in plane peak, and A1G, it is out of plane peak. So we can see that after functionalization, this peak became much more intense and wide, which says that our material was functionalized successfully. Here we can see the chips which we used and their geometry with all the dimensions. So we used polyethylene terephthalate substrate, which is shown on left side with already deposited chromium chips with geometry which we can see on the right side. After that, using drop cast technique and the electrophoresis method, we deposited our material in these chips. After that, we conducted photo detection experiments. But before, we first of all took IV characteristics. So in these IV characteristics, we see that here photoconductive photodetection mechanism is taking place. Then, in case of a photodetection experiment, we used 3 bias voltages. I mean to say 5 volts, 7.5 volts, and 10 volts. In case of 5 volts, we can see that in case of pure material, our photodetector can detect only 51 milliwatt per centimeter square, 100 milliwatt per centimeter square, and 150 milliwatt per centimeter square. But when we are applying higher bias voltage, for example 7.5 or 10 volt, in that case we can detect power density of light with 32 milliwatt per centimeter square. So as we can see from the line B and figure C. After that, we performed the same set of experiments with functionalized TIS2. So we can see from the IV graph that the photo detection mechanism is completely the same as in the case of pure material. But in case of photodetection experiment, we can see that even with 5 volt bias voltage, our photodetector can detect 11.6 milliwatt per centimeter square. It means that our photodetector became much more sensitive. After that, we made a comparison table of our sensitive element and some other sensitive element from the transition metal chalcogenides family and made a comparison. So here in red circles you can see the characteristics of other photodetectors which are worse than of ours. So in conclusion, I would like to say that the functionalization of our material was made successfully, and that all the characteristics became much better than they were in case of pure material. So you can see on this slide also some other parameters which we calculated. I mean to say, for example, sensitivity, quantum efficiency, and detectivity, which I also mentioned in the table on the slide before. So here there are some references, and thank you for your attention. If you have any questions, I would like to answer them.
Very short and impressive talk. And now it's open for questions.
Can you show your slide with Raman spectrum? After functionalization, you have a strong baseline. Why do you conclude that your structures were functionalized? How do you deduce that?
We proved the functionalization because the baseline shifted up because of presence of silver. So that is why baseline also shifted up.
Silver nitrate, it's silver particles.
Silver nitrate.
But silver particles, metal particles usually enhance the signal, and that is very strange. Why silver nitrate enhances the signal?
Maybe because in silver nitrate we also have silver nanoparticles. Probably during ultrasonication, because we use quite a high power sonication probe, maybe something happened in case of silver nitrate itself.
It seems like you have PL, photoluminescence signal. Maybe that's the reason for the very high baseline.
Yeah, I think that we should make also this characterization in case of photoluminescence. Thank you.
Thank you.
Our question?
Thank you for your presentation. I have a question. What is your band gap of your titanium disulfide? Band gap of your materials?
Here?
Yeah.
Can you repeat, please?
What is the band gap of the titanium disulfide?
In case of this specific one sample, we've got a band gap of 0.43 electron volt.
Thank you. What is the thickness you said that you have a titanium disulfide nanosheets. So what is the thickness of the titanium disulfide nanosheets? So I see here it looks like micron.
Yes, we didn't measure exactly the thickness. We saw that there are the structure which we needed, but we can make a rough estimation from the picture. So I assume that it is around 5 micron, probably.
Okay.
Just rough description.
Thank you. I think you should exfoliate it, so we should be better. Last question. Did you try to bend?
Yes, we tried bending.
How did you make the contact? How did you make the contact? Because when you bend the contact, you also that can decrease the signal.
I think that we need to make a study with the cycles of bending also. In this work, the main task was to make materials on the flexible substrate so that it will work, and after bending, its properties didn't deteriorate.
After bending or why bending?
After bending, like we bend it, then again measured, yes. So it means that we can apply our sensor on some curved substrate, and it will not lose its properties.
Thank you very much.
And what do you think about commercial perspective of your photodetectors?
I think it have good perspectives, because especially if it can be used in aerospace, and also in case of continuous monitoring of human health. For example, it can measure continuously temperature, and if person is sick and we need to measure his temperature for a long time without any breaks, then we can use it. And in case of gases also, for example, we can put one source of infrared light and one this receiver of infrared light. So in such a case, by absorption of gas, I mean to say, by reducing of intensity of light when it is propagating through the gas. In such a way, we can see what gas is here and in what concentration. Just lots of study must be made to see so that no cross-selectivity will be here.
Okay, last time speaker. Oh, very short.
This question. What approximate detectivity you can expect from your material? And
in table?
Approximately, in order of magnitude, detectivity.
Yes, I understand your question, and detectivity is shown in the table.
It's not the detectivity.
Sensitivity.
This is sensitivity.
Sensitivity. Какая чувствительность наша?
Because detectivity include the time rise time.
Yeah, here in the table we calculated detectivity also. So it is in the power of 13 of joules. For 10 in the power of 13 joules.
Minus. Minus something.
No, not minus. 10 in the power of 13.
Okay, probably you can discuss what the share of detectivity, sensitivity of the session. So let's thank the speaker again. And the last talk of our present session will be presented by, I guess, at this case, Dr. Sergei Dalenko from Moscow State University. Thank you.
Если я уменьшаю количество фотонов, человек, который еще вместе это неделя лежат. Поставлю. Последний.
Что, есть надежда?
Да, сейчас.
Спасибо.
Еще максимизировать его совсем.
Наклейки реагируют? Давайте я буду перевести тогда. Не говорите, я буду перелистывать просто слайды.
Good day, ladies and gentlemen. First of all, I would like to say that those of you who came here to listen to the talk of Tatiana Dolenko, which is stated in the program, you will have this opportunity tomorrow morning. There is just some mix-up connected with the coincidence of the family names. And my name is Sergei Dolenko. I represent our joint team from Physical Department and from Institute of Nuclear Physics from Moscow State University. And what we do is application of methods of machine learning to the data of spectroscopy. And I would like to tell you some interesting facts in this way. Next slide, please. As you know, inverse problems are the type of problems that require to restore the system parameters from the observed data describing the system state, and the problems, the inverse problem of spectroscopy is getting information from spectra which are observed. In this study, we consider the problem of determining the concentrations of inorganic ions in water by Raman infrared absorption and optical absorption spectroscopy. Next slide. Yes, this topic is very actual because determination of concentrations of substances is required in environmental monitoring, industrial and wastewater monitoring, quality control of beverages, and so on. It should be noted that this problem is required to be solved in non-contact express mode with acceptable precision. Next slide, please. Therefore, traditional chemical methods, which really provide a high accuracy, not always fit because they are contact, and each test requires substantial time, and there are also some other drawbacks listed here. Therefore, spectroscopic methods are considered as an alternative. Next slide, please. They are expressed, first of all, if we use laser, for example, Raman spectroscopy, they are non-contact, and the base for the use of such methods for determination of concentrations is that the shape of the spectra of a solution is highly sensitive to changes in its ionic composition and to the concentrations of ions. Unfortunately, if we deal with liquids, the spectra are quite complex. They have usually have wide bands with nonlinear interactions, so it's not a very simple task to get the concentrations. Moreover, at this moment there is no adequate mathematical model
that could help us solve the direct problem, that is to describe the changes in the spectral shape depending on the concentrations of the components. You have at least several components in the solution. So for processing such data, we suggest using methods of machine learning. Next slide, please. Here I state the integration of methods of spectroscopy. We use data of different types of spectroscopy simultaneously, and here is the justification for such a case. Various types of spectroscopy represent the required information, each in its own way, so we may hope that combining such information from different spectroscopies may help us improve the quality of the problem solution. However, many machine learning methods are sensitive to the number of input features, and if we just combine several spectra at once, the efficiency of the integration may not be as high as we hope, so it needs to be tested in real experiment. Next slide, please. So I'll demonstrate the results on two databases, both dealing with heavy metal ions, a very topical area, detection of heavy and determination of concentrations of heavy metal ions. The first database combined Raman and optical absorption spectra. The cations and anions are listed here. pH value was also measured for each sample. Such anions and cations were fully dissociated, so the salts are listed here, but in fact we should really speak about ions. The database contains 3,500 of solutions, so this database may seem large from the point of view of experiment, but it's not so large if we speak of machine learning. The concentration ranges are listed here. Next slide, please. Here is the short description of optical absorption experiment. The spectrum was recorded in 800 plus channels. Next slide, please. Here are typical spectra of optical absorption. We can see that the bands of cations of heavy metals nearly don't overlap, and so this makes good grounds for determination of separate each of these ions from the same spectrum. That's not the case with the complex anions, unfortunately, and as we will see, this is the reason why it's not so good with them from this type of spectroscopy. Next slide, please. Raman spectroscopy, here are some lines about the experiment. We recorded the spectra in two spectral ranges, and total it was 2 plus 1,000 spectral channels, some preprocessing, suppression of the pedestal analyzation. Next slide, please. Here is a typical spectrum. To the right, you can see the valence Raman band of liquid water. To the left, we see the deformation band, and also two narrow peaks corresponding to proper vibrations of sulfate and nitrate ions. As for cations in Raman spectra, they influence the shape of the Raman valence band, so this is where can we get the necessary information from. Next slide, please. Now, a few words about machine learning methods. I won't get in more details. If someone is interested, I will be glad to tell it to you in the break. But here is the list of the models we used. There were neural networks, these conventional multi-layer perceptrons, gradient boosting over decision trees, random forest, and several types of linear regression. Also, we tested method ensembling, that is, averaging of the results of different machine learning models, weighting, and also the so-called stacking, when we have a meta model combining the results of several models and giving the final answer. And it was a simple neural network. You should also know that we use autonomous determination, that is, that each of the 6 parameters was determined separately. Next slide, please. Here is the just global list of results for cobalt cation. From top to bottom, we see the results of Raman spectroscopy, absorption spectroscopy, and of integration of both methods. And we see that the mean absolute error of concentration determination is small for absorption. This is the result of the composition of the spectral bands of cations. And on the contrary, it is worse for the Raman spectroscopy. But it's interesting that integration does not help us in this situation. The results for the integration are somewhat worse than the results for absorption alone. From left to right, there are the results of different machine learning methods, and the arrows mark the best results obtained. We can also see that ensembling also in this case is not very effective. The finally best results are obtained by random forest with somewhat deep trees. Next slide, please. This is the same type of results, but for anions, for complex anions, sulfate, and you see that the results are on the contrary. They are worst for the absorption spectroscopy, and they are best for Raman spectroscopy. And as for integration, it nearly doesn't work. The results are nearly the same as for Raman spectroscopy, or just a bit better than for Raman spectroscopy alone. And the next slide, please. And these are the results for pH. Here you see that the results for Raman and for absorption spectroscopies alone are comparable. And so the integration works. The results obtained with both methods used simultaneously are better than for each of the methods used. Next slide, please. The second database was somewhat more serious. We have a larger list of cations here, the same anions, nearly the same amount of solutions, a little larger, and a larger concentration range. You see that the mixtures themselves may be more complex, containing up to 8 ions simultaneously. Next slide, please. A few words about experimental setup for optical absorption spectroscopy, nearly the same as in the previous case. Next slide, please. Next slide, please. Here are the spectra. You see that for this type of ions, it's not so good as in the pristine case, but it's more realistic. Usually the bands really overlap. Next slide, please. Thank you. The infrared absorption spectroscopy, the new one we used for this database, measured by Bruker spectrometer, and no preprocessing post-performance, 2000 channels. Next slide, please. And these are typical IR absorption spectra. We can also see the valence band of water here, and some proper bands of the ice that we determined. Next slide, please. And this is for Raman spectroscopy with a laser excitation, Yak laser. Next slide. And again, the left and the right bands of the spectra, Raman valence band of water, and the proper bands and the deformation band of water. Next slide, please. Next slide, please. The machine learning set of methods was nearly the same as in the preceding case, a little smaller. But here we tested several types of integration, each of the three methods separately, any pair of methods, and all the three methods at once. Next slide, please. Here is the set of the results. From top to bottom, there are the results for three machine learning methods: neural networks, gradient boosting, and random forest. And what is most interesting, from left to right, we see various combinations of spectroscopy data. Separately, Raman, IR, and optical absorption, and pair combinations and total combination. And here we see that nearly in each case, integration of data of various spectroscopy methods really works. We see that the best results are usually obtained either with pair combination or with all the three methods at once. Next slide, please. Here are the conclusions. Machine learning is an efficient set of algorithms that can solve inverse problems of spectroscopy. Integration of data of several spectroscopy types is not always effective, but sometimes it is, and to be effective, integration should be applied to data of the types that provide compatible performance if used separately. If one type is much stronger than the other, then please use the best single type of spectroscopy. And this conclusion holds both for various machine learning methods used over this spectroscopy data, and also for integration of the machine learning methods themselves. Next slide, please. Thank you for your attention.
Thank you for the presentation. Probably we have for one question time.
Thank you. Thank you, Sergey. Can you estimate the detection limit of ions which system media?
Sure, it depends on the possible combination of ions. Usually it is about from several tenths of mole per liter to several hundredths of mole per liter for different mixtures. We have several databases, not only those I've told you about, but also the databases with about 10 different inorganic ions. So it really depends first on the experimental precision of the apparatus we use, and second, on the combination of the solution itself. But not the machine learning methods are the source of the error. The main source of the error is experimental as usual.
Okay,
thank you.
Very short. So let's say you prepare algorithm for machine learning for identification of impurities in water, in pure water. But would it work in case of tap water or water with organic impurities for real sample?
Thank you. A good question. It definitely works with types of industrial waste when the concentrations are high. We tried and it worked with many types of mineral waters, but it nearly doesn't work for tap water because the concentrations are too low. At least at the present state of our experimental equipment. Possibly it could be improved, but it's quite expensive.
Thank you.
Okay, thank you. I'm sorry, Sergey, I must cancel discussion and because we are out of time. So our session is finished. Let's thank all the speakers. And the next session will be held at which time?
We need to postpone a little for 15 minutes. will delay.
No, it will be. It depends on organizers.
No, I think the next session should start on time. Otherwise, we will break everything. Half fun too. This is the start of the next session. We have almost an hour.
The next session will start at 14:30.
Yeah.
So the next session will start
in time.
In time.
Знаете, мне что-то показалось,
Да, не, просто я немножко подобно сейчас мучаюсь.
Хоть объявите хоть как-нибудь.
Значит, выходите из здания, идете налево и обходите вот этот квадрат. И когда поворачиваете, там
Мы же можем. Не, он такой больше этот философский. Вопрос Не, я не как раз понятно. Вот смотрите. Вот картинка. Вот это вот у вас реальный да, уже окончательно установлено.
практически чисто.
Да, вот эти вот точки, если я правильно понимаю, это эксперимент. Смотрите, вы говорите, что вы берете только вот эту начальную часть, да, и тогда вы можете определить концентрацию. Да, я понимаю. Казалось бы, вы можете спокойно решить в клиентном случае все уравнения, в данном случае, наверное, вообще. Почему не можете? Подожди, а вот если мы возьмем сферически, знаете, двухуровневую среду, двухуровневый атом, классику, просто начнем с него. Наверное, нет, я экспериментатор, поэтому.
Нет, есть индивидуальные задачи решаются почти. Если возьмем те же блоховские
Нет, численное.
Если у вас будет...
Хотите сказать, если я возьму двухуровневый атом, численно его решу, то есть у меня, в принципе, получится вот так.
Да, это блох дает.
Да, это блох даст.
И матрица здесь.
Да. А назад я не смогу. Слишком много подгоночных параметров получается, чтобы сойтись.
Невозможно. То есть это большие программы действительно для прямой задачи.
Нет, ну ладно, я на ноутбуке такое считал. Это вот по типу подобных, блоховских, для двухуровневого атома. Математики там.
Существует. Сейчас вообще библиотек много.
Сейчас
я сам обычно.
Вот, но поскольку блоховские уравнения,
Не, библиотеки есть, просто там разбираться надо.
Вот, но прямые задачи. Я не говорю, что мы...
Обратно, ну все, я понял.
Да. Вы знаете, вы даже обратную задачу для выращивания аппаратных функций решается с вашим трудом. Другой вопрос. Я его не стал затевать.
Вас уже знает. Вы перефразируете в таком виде. Давайте вас.
Здесь мы используем интегральный аппарат.
Не видал, не видел.
Я ни в одной книжке этого не видел, ни в одной статье. Всегда все занимаются тем, что решают обратную задачу. Да, потому что надо.
У вас PDF, да?
У меня есть и та, и другая версия, но лучше PDF, что здесь PDF. Потому что если докладчик видит, я думаю, что у него там что-то схемы, картинки.
Тебе интересно.
Ну это, знаете,
сейчас давайте посмотрим, что
последнее время получается. Это лучше, потому что
меня совершенно понятно. Тебе не стало.
Ну, я да, посмотрю.
Вообще-то у нас побочный продукт.
Видно, да. Текст есть. Главное, не
Да.
Основная часть нужна, если какие-то будут нюансы.
Ну, если что, так же.
Лучше, конечно,
конечно.
Так, чётку я не слышу. Так,
Отбирается он при каждом проходе. Получается, что вот этот
ну это да.
Еще будет.
Да. В кювете там еще.
Он еще подсвечивает.
Там еще будет.
PDF, наоборот, лучше с 5, лучше стабильно работать. Стоит программа для PDF. Шишкина, да? Так, кого нету сейчас?
Я вот как-то вам отвечал.
Я вот да, еще спрошу.
Нужно, я дам режим докладчика, и нужно вот справа демонстрировать ваш экран, запустить презентацию и выбрать Windows, окошко презентации.
Спасибо.
Первый у вас?
Так, что, Леонид Анатольевич, вы как, это кушаете?
Я сейчас пойду.
Я не пришел, но вчера звонили в самое, и не мог понять, что нам про говорит, да, и в итоге понял, что вы все время мне про Волгу. А я думаю, что это за заведение такое? Как же оно так называется? Это Волга. Река Волга.
Это река, вот ее видно здесь.
Течет река Волга. Так, ну что, пошли? Я знаю, что наши коллеги уже заняли место в одном заведении, которое называется
Видимо, нажали выключатель. Возможно, случайно нажали выключатель и выключили его. Да, поэтому не работает. Хорошо, пробуйте. Влево, вправо, вправо, следующий стоит. Лазером здесь, к сожалению, показать не получится, потому что LED-экран слишком яркий, да.
Это остается.
Да, здесь.
Оба они сейчас
Долго держится, ну, секунды, 2-3.
так и так, да? Работает.
Да. Также вы подержали немножко. Ну, включается, он не нужно долго держать, сейчас продолжим держаться. Сейчас потребуется здесь. Ну, если будет вопрос, я помогу.
Хорошо.
Оставлять здесь.
Все ушли. Спасибо.
multisite.
Может, только, знаешь, косяк, что чел выходит из-за камеры.
Я уже забил, я, короче, на эти две работы.
Я смотрел твою трансляцию, смотрю, они у тебя что-то и там стоят, и туда.
А мне что делать? Мне
Как ты их
либо
вообще
там рулить или вот этой камерой. Я к ней подходил. Они вот так ходят,
Ты вот той стал захватывать?
Это перегревается камера.
Надо мою поставить, у меня есть третья же. А что, не собирался? Я думал, я сейчас...
Мы рассчитывали, что он здесь будет стоять, а здесь никто не стоит, один чувак стоял.
А что они не стоят?
Не знаю, неудобно.
Еще самый прикол, есть в PowerPoint лазерная указка, которая показывает, и у тебя там сразу все рисуется. И
Здесь PowerPoint, оказалось, нет. Мне пришлось быстро собирать ноут, да.
Реально?
Нет PowerPoint. Это чистый комп.
Нет. Ну все.
И, видимо, эта студия новая, даже ничего не накатывали его.
А что ты тут телек отключил?
А, презентацию скидывать, да? Презентацию нет, да. Первый, да? Это. Последний.
Сейчас они. Вот сейчас не можешь включить. Все на английском, да, продукция?
Говорили один на русском так подпись. Да, ну сейчас надо спросить свой. Ну, мужик, но, видимо, не особо знает, не просто листочку читал.
Ну вот я тоже только так не понял.
Ну, Прiezzhev на английском.
Прiezzhev на английском.
Ну, индус, он был модератором, говорит, ладно, говорит, можете говорить, я все равно могу презентацию покажу. О чем речь? Александр, вас видим?
Отлично. Слышите?
Да, слышим.
Супер. Начинаем. Единственное, я эхо своего голоса слышу.
Кого?
Эхо слышу своего голоса.
А, это мы отключим это, когда вы выйдете на связь.
Отлично.
Да, у меня вопрос, знаете, по кому? Целиков Лев.
Нет.
Не будет его отсутствовать?
Нет, больше сведений нет, я сам хочу знать, что будет. Не загрузился. Остальные есть, ну, что там по порядку?
У нас первый ВПС.
Так, Кушнежик есть?
Есть. Вот целик вопрос по презентации. Павликов есть и Пятеркин есть. Только единственное, что его ассамблея нету Целикова, или он просто презентацию не принес, или вообще он отсутствует. Сейчас это соберутся до уточнения.
Дополнительную информацию. Крайне неприятно. Ну, это, конечно, сильно зависит от того, какой будет. Попробуй. Попробуй. Да, давайте. Кто? Ну посмотрим. Используйте.
Сейчас пожалуйста.
Александр, вы тут? Александр?
Я так понимаю, председательствуете? Ну, я тут вот с вами за компанию.
Ну, давайте вместе председательствуйте.
Ну, лучше вы председательствуете, потому что я не особо являюсь специалистом в данной области. Я, конечно, посижу. Так что, если что, я как бы...
Тут, да, сменится, если... Рука бойцов в колодце.
Лучше здесь все.
Сейчас начнем.
Собственно, у нас всего 4 или 5 докладов, так что, возможно, все уже есть.
У нас нет возможности.
Мы еще кого-то ждем? Или все уже оставшиеся? Еще ждем?
Да, сейчас там еще чуть-чуть подождем.
Он все
Да.
Здравствуйте. Everybody in this room, and we are ready to start. The first talk will be given by Priezzhev, and this is an online talk, so please start the presentation.
Okay. Do you see me? Do you hear me? So, dear colleagues, do you see my slides? Is it okay?
Скажите, что видите?
Yes, we see everything. Please start.
Okay, thank you very much. First of all, I want to thank organizers inviting me to this conference. I need to apologize that this year I cannot come in person, so I have a rather unexpected and solid reason to stay at home with my family. And my name is Alexander Kuchmizhak, and today I will be speaking about optical nanosensing enabled by advanced laser technologies. And this is an outline of my talk. I will start from the brief introduction, just reminding you the basic concept of optical nanosensing, where you can use the surface-enhanced Raman scattering and surface-enhanced photoluminescence effect for detection of different molecular species. And then in the second part of my presentation, I will generally focus on our recent experiments on fabrication of functional nanostructures for optical nanosensing devices based on generally two advanced laser nanofabrication technologies. It's a laser ablation in liquid and laser-induced periodic surface structure. And finally, I will conclude my talk with a short summary. So, okay, let's imagine some molecule in a free space or in a liquid, and if we will shine the laser into this molecule, most probably we will see the relay scattering with the wavelengths that exactly the same wavelengths as the incident radiation. And if the molecule possesses some photoluminescence response, we were able to see the photoluminescence signal, and there is a rather small probability to excite the so-called Raman or inelastic scattering. Typically, the probability is 1 photon over 1 million incident photons to excite the Raman scattering, and this scattering reflects the excitation of the certain chemical bonds of the molecule. So with this characteristic Raman scattering, one can identify the chemical structure of the molecule. But actually, the signal, especially Raman signal, is rather low. But both the photoluminescence and the Raman scattering can be significantly increased when attaching the molecule to the nanostructure substrate, typically made of noble metals supporting surface plasmons. And generally, these effects come from the interaction of the molecule with enhanced electromagnetic field created by these nanotextured surfaces or nanotextured structures. And especially for Raman scattering, the signal enhancement coming from the electromagnetic contribution, that is the force power of the electromagnetic field amplitude, plus chemical contribution. With both this contribution, we can achieve the enhancement factor up to 10 in order of 15. That is actually enough to detect even a single molecule attached to the surface. As far as I mentioned, the most common way to design the good sensor with this surface-enhanced Raman scattering and surface-enhanced photoluminescence effect is to design the appropriate nanostructures that will be localizing your electromagnetic field within the confined spot. And there are common, of course, common examples how to achieve the field localization. For example, it's a sharp features, it's nanoparticles, it's small gaps, and also, we don't need to forget about that in typical sensing experiments, we have the laser beam that can be focused within the focal spot that is diffraction limited. And within this focal spot, we need to ensure as much as possible numbers of these electromagnetic hotspots created. And of course, there are multiple methods to design and to fabricate diverse functional nanostructures for for enhancement of the electromagnetic field. And I'm happy that in this conference, I don't need to agitate for advanced laser technologies. We all know these laser technologies are rather flexible. They're cheap and high performing and provide remarkable ways to design different nanostructures. However, from basic consideration, we cannot focus our laser beam into the focal spot that is restricted by the fundamental diffraction limit. And of course, we have also the thermal effect that further decrease our fabrication resolution. So the general consideration from this, that it's hard to produce nanoscale structures by direct laser nanofabrication in a similar way as, for example, you can do it with the electron beam or ion beam milling procedures, where you can confine your beam within the nanoscale volume. And actually, when you confine the laser energy within a rather short laser pulse and interact this pulse with the material, the interaction of this laser pulse with the material can be very specific. And first technology I want to highlight as a promising to design and to fabricate the functional nanostructures for optical sensing is laser-induced, it's a laser ablation in liquid, where you just shine your laser pulses into the target covered by some liquid, And with this, you cause ablation of the material, and the liquid medium collect the ejected product in the form of the nanoparticles. And the method is very simple, and in some cases, you can exclude all the chemistry, just use some non-reactive liquid environment and the target to generate the nanomaterial, so you can produce a chemically pure nanomaterials. Also, we can provide a very nice and very unique synthesis conditions that is impossible to achieve during, for example, chemical synthesis as high temperature and GPA pressures. And also the method is rather flexible regarding the choice how you generate your nanomaterial. So you can ablate the material target, you can then remove the target and continue to irradiate your generated suspension for their fragmentation or reshaping. And also, additional opportunity is generation of hybrid nanomaterials just by ablation of a multi-material target, or by mixing colloids of different made of different materials and irradiate this mixture of colloids. And with this, you can achieve the unique hybrid nanomaterials with shared material properties that provide you opportunities to expand your functionality of your sensor devices. And in search of such functional nanostructures for optical nanosensors, we try to design the gold silicon nanoparticles, where the gold represents the main plasmonic chemically stable material, and the silicon is a common semiconductor. So we find this idea as good to design these hybrid nanomaterials. And first, we generate the silicon nanoparticle just by ablation of crystalline silicon wafer by nanosecond laser radiation in isopropanol. Then we remove the target, add the tetrafluoroauric acid that serves as a source of metal gold ions, and continue to irradiate the suspension in the presence of this tetrafluoroauric acid until we achieve the hybrid nanoparticles with the general structure where we have the nanocrystals of silicon wrapped and decorated by the small gold nanoparticles. And by making the focus ion beam slicing and imaging of this kind of nanoparticles, we found that the structure of these nanoparticles is generally the silicon nanocrystals are located near the interface, while the center of this nanoparticle is mainly made from the gold. And the synthesis of these hybrid nanoparticles starts from decoration of the pure silicon nanoparticles by small gold clusters upon thermal reduction of the acid precursors near the interface of these silicon nanoparticles, because only in the solution, only the nanoparticles absorb the laser radiation, so they hit much more strongly than the transparent solution. Once we increase the radiation time or number of applied pulses, we also increase the amount of the decorating nanoparticles. They start to fuse together and melt the silicon beneath. And finally, in the molten phase, there's a mixture of the gold and silicon. But in the solid phase, there are no solubility of gold in silicon. So upon resolidification, the silicon tries to form the nanocrystals, pushing away the gold, so the gold occupies the space between the formed silicon nanocrystals. The centralized powder demonstrates a very nice and broadband light absorption, facilitating the enhancement of the electromagnetic field upon excitation by laser radiation. And also important to stress out that actually, as long as we have the silicon in nanocrystalline form, we have the Raman signal from these nanocrystals, and this signal allow you to measure the temperature at which the particles will be heated by upon excitation of Raman signal, like shown in this slide. And as we found that the increased amount of the gold in these nanoparticles increases the heating efficiency of these nanoparticles. So for the fixed pump intensity of our laser radiation, we can actually control the maximal temperature at which the nanoparticles will be heated. And this story is rather good when we consider the ability to detect some molecules absorbed onto these nanoparticles, because we can simultaneously detect the Raman bands of the molecules attached to this nanoparticle and the thermal sensing band that allow you to actually to find the position of the nanoparticle, to calibrate the signal, to actually correlate the signal enhancement coming from the silicon nanoparticles and from attached the molecules, just to make some analysis. And more importantly, that actually can by controlling the temperature, by checking the position of this temperature sensitive band, you can also avoid to overheating of your molecules to avoid their thermal degradation. And with this experiment, we detect by surface enhanced Raman scattering the typical amino acid tryptophan functionalized onto the surface of the nanoparticle, and we found that at low intensity, we have even more stronger Raman signal from the molecules than at high intensity, because at high intensity we already reached the limit of thermal decomposition of our analyte molecules. We can, of course, we can design some fluidic device to inject different types of the metal precursors to generate different nanoparticles to control their general morphology, like a pure hybrid, like core-satellite nanoparticles. We can control decoration degree as we did in this work, where we generate the silicon nanoparticles decorated with silver nanoclusters. And of course, these nanomaterials can be applied for detection, not only for detection of the molecules, but also for detection of some molecular transformation, as we can, as you can see here, for example, in these experiments, we detect the dimerization of monomers. It's a paramine thiophenol to dimer molecule, dimer captazobenzene. And you can detect this process by tracing of appearance and the rise of the intensity of 4 additional bands associated with dimer molecules. Okay, so let's go to the last part of my presentation. And as far as I mentioned, the fabrication resolution is limited by diffraction. So the feature size of about wavelengths can be achieved by direct laser printing. However, when we use the ultra-short or femtosecond laser pulse, there is a chance to excite the surface waves, and the interference of the surface wave with the incident radiation allow you to produce the interference pattern with the characteristic feature size that is wavelength divided by effective refractive index of the surface wave supported by the dielectric material interface. In some cases, we can excite surface waves much more efficiently, so the interference becomes dominating in this process, and the feature size will be expected to be twice lower. So it's a doubled wavelength divided by doubled effective refractive index. So with this, we already can achieve the size of about 100 nanometers. And we cannot, of course, forget that laser radiation can induce melting of the material, and there is a lot of hydrodynamic instabilities that can be developed within this molten layer of the material, and the instability wavelengths that is defined the feature size can be much smaller than the incident laser wavelengths. So all set of these described phenomena allow to generate diverse nanostructures, typically called laser-induced periodic surface structures, that we have found to be a universal phenomenon observed on diverse materials. And in search of actually, our group work a lot on production of laser-induced periodic surface structures on different materials, but I want to highlight the practically relevant case for optical nanosensing. We studied the femtosecond laser processing of silicon, just crystalline silicon in isopropanol, and we found that upon few pulse excitation, we can generate the nanogratin with the period of about a half of the wavelength, so it's 250 nanometers. But when we just continue to irradiate this substrate, we reduce the period to about 70 nanometers, so it's a wavelength divided by 7. And we developed the model to describe this process because this periodicity is deep sub-wavelengths, and this model involves the formation of the nanogratin with a period of 250 nanometers, and this process is can be explained by interference of the incident radiation at the surface wave, and then the related early hydrodynamic instability reduces the period of the formed nanogratin down to 70 nanometers. Okay, so upon this procedure, we can generate the high aspect ratio nanogratins with nanogaps that can be then coated with the metal film to control, to provide the plasmonic response and to further reduce the gap size to ensure high field localization and enhancement in the gaps. And we found that we can achieve very nice surface Raman scattering enhancement with the signal enhancement up to 10 in order of 9, very uniform distribution of the enhancement factor over the textured area. And of course, this substrate can be used for detection of the molecules, for detection of the molecular transformation. But generally, this hybrid semiconductor metal nanogratins can be fabricated during a single-step procedure. Namely, for example, we can make texturing not just in the pure isopropanol, but we can also add some metallic precursors like a silver nitrate or tetrachloroauric acid. And upon texturing and formation of the nanogratin, we can also generate the nanoparticles that will be embedded into this formed nanogratin. And by controlling because we need to apply a fixed number of laser pulses per site, we can control the decoration degree with metal nanoparticles by controlling the amount of the metal precursors in the working solution. And one unique opportunity we can achieve with this is thermal reduction of the metallic precursors to nanoparticles is generally achieved within the focal volume of our laser beam. So we can fabricate the nanogratins locally decorated with different metals, and we control this decoration at micro scale. Okay, probably the last experimental slide. We try to apply these technologies, this nanogratin decorated with metal nanoparticles for detection of mercury ions in water. And to do this, we use the molecular probe. It's actually a derivative of rhodamine molecules, specially functionalized to react on the presence of mercury ions in water by increasing their photoluminescence. So this probe was developed in the group of Professor Svetlana Bratskaya from the Institute of Chemistry. And this probe allows, just in working in the bulk solution with the molecule, allow to achieve the 10 nanomolar limit of detection of mercury ions just by detecting the change of the photoluminescent signal from this molecule. But we go further and design some kind of fluidic device where we have the sensing area contained a nanogratin functionalized with this sensing molecule that can be pumped from the top, and we can detect the fluorescence from the molecule attached to this nanogratin. And with this nanotextured area providing a very strong surface ground photoluminescence effect for the molecules attached, we achieved the limit of detection of mercury ions of 0.50 nanomoles only. So it's probably the best result for the most sensitive sensor for the mercury ions reported. Okay, so I want for conclusion, I just want to say that today I try to convince you that direct laser processing and laser ablation in liquid provide you remarkable opportunities to generate the hybrid functional nanostructures. You can upscale this fabrication process from the isolated nanoparticles to nanostructured surfaces, and even design more sophisticated sensing devices. Many thanks to our guides, to our collaborators, and all of you for your kind attention. Thank you very much.
Thank you for interesting talk, and it is now open for discussion. Please, questions. Yeah.
So thank you very much for the nice and interesting report. I have two questions. So first, why you choose to use silicon and aurum nanoparticles to create such interesting composite substrates? Why do not you use another kind of semiconductor, or not aurum nanoparticles but something else? And what's the difference between enhancing of SER signal from these nanoparticles and compare with clean pure aurum nanoparticles? And the second question is how do you measure the surface activity of such suspension? Because nanoparticles locate in suspension, and do you measure inside the suspension? Or maybe you dry it on some substrate? So what's the methods of measuring? So thanks.
Okay, many thanks for question. I will start from the second question because it's easy to reply. Actually, what we did is functionalize, so we put our suspension of the nanoparticles, mixed it with the suspension of the molecules, wait, for example, several hours or one day until the molecule attach the nanoparticles, and then we just deposit the our functionalized nanoparticles onto the substrate. So we did not measure the signal in the solution. So we measured it on some substrate. For example, we can typically use something like a gold mirror to deposit the nanoparticles. The second part of the question, we try to produce the different composition of the semiconductors and plasmonic counterparts. And probably a few years ago, we published a paper where we mixed the gold nanoparticles or silver nanoparticles with titanium dioxide. That is also a very interesting work. But for this work, I try to highlight that there is a good scene when we try to mix the gold with the silicon, because silicon have the slightly different properties. For example, it have the Raman band, which allows you a temperature feedback modality. Also silicon, I did not mention this in my presentation, also silicon can be pumped from the gold part to excite the nonlinear photoluminescence. So it's also provide you a broadband signal for diverse application. And probably the part of the question was what is the benefits of using these hybrid nanoparticles instead of just pure gold. In terms of surface enhancement, probably there is no huge difference between the pure gold nanoparticles and hybrids you can achieve. And probably with small gold colloids you can achieve even better surface enhancement, but you cannot provide it with the temperature feedback modality, as I mentioned.
Thank you.
Thank you for your presentation. I would like to ask you about the silicon nanoparticles. So what is the smallest range of sensibility that you can detect the temperature with silicon nanoparticles? Because as I see that you have a range about 300 degrees, could it work to about the range of human body?
Actually, the detection limit is it's very high because silicon can be heated up to thousands of kelvins. So it's you can detect high temperature. But the question probably how accurate you can detect. Yes. And the accuracy of detection is generally related to the ability of your spectrometer to check the shift of this Raman band. So generally, for common spectrometers, you can achieve the accuracy of about 0.5 reverse centimeters. So if you recalculate it into the temperature, so it will be about 20 kelvins.
Thank you. More questions? No more questions? Let us thank the speaker again. And yeah, next talk will be given by Professor Shuleika. Please.
Thank you. Good day, dear colleagues. Here is the title of my talk, Optical and Structural Anisotropy Induced in the Thin Amorphous Films of Chalcogenides and Silicon by femtosecond laser action. What? How to... No, it's on. Oh. Тут красная лампочка горит. Here is the outline of my talk. In the introduction, I'll talk about the perspectives of femtosecond laser writing of laser-induced periodic surface structures on thin amorphous films of chalcogenides and silicon. Then I talk about our experiments on the irradiation of chalcogenide and amorphous silicon films by femtosecond laser pulses, about the formation of the surface relief and modeling of its formation and evolution, and also about some properties induced by the formation of this surface relief in the samples. Direct laser writing is a powerful technique to fabricate various materials such as both dielectric and semiconductors and metals, both in the 3D and 2D with submicron accuracy, and you can achieve even nanoscale accuracy, but for this you need to use some additional techniques, and one of them is formation of laser-induced periodic surface structures if you apply ultra-short laser pulses, namely femtosecond pulses with high power. In case of semiconductors and dielectrics, the formation of femtosecond laser-induced periodic surface structures is caused by the interference of, well, in general, the formation of these laser-induced periodic surface structures, or LIPS, is induced by the interference of surface plasmon polariton excited by the incident radiation and the incident radiation itself. And in case of dielectrics and semiconductors, the surface plasmon polaritons can be excited due to generation of electron-hole plasma by the incident laser radiation. In case of the amorphous silicon or chalcogenide films, the formation of such LIPS is also accompanied by phase transitions, and the chalcogenides are well-known phase change materials which are widely used. For example, optical memory is based on the chalcogenides, the rewritable optical memory. And the laser-induced periodic surface structures combined with phase transitions can induce optical anisotropy in these materials, namely birefringence and dichroism, as well as electrical anisotropy, because the crystalline and amorphous phases, electrical conductivity also differs. And such structures can be applied as polarization sensitive devices, for example, in the infrared optics. And thus, our aim was to work out the technologies to fabricate laser-induced periodic surface structures combined with the simultaneous phase transformations of the irradiated film on large scale areas, and to study the properties of the formed structures. And we chose the chalcogenides such as arsenic, selenide, and arsenic sulfide. They are transparent in the near infrared region and have high refractive index in that region. Also, we aim to explain the evolution of the formed laser-induced periodic relief and explain the in-plane anisotropy registered in the amorphous silicon films, anisotropy of conductivity. And at the first stage of the experiment, we need to determine the regimes of laser irradiation to produce laser-induced periodic surface structures. And for this, we irradiated an array of single craters on the surfaces of chalcogenites with varying parameters of laser radiation, namely the number of pulses per crater and the energy of laser pulse. On the irradiated surfaces, we can observe various types of formed lips, and here are the main types. The first one is high special frequency lips, so-called HSFL, which are parallel to laser polarization and have periods several times smaller than the laser wavelength. The second type of structures is low special frequency lips, or LSFL, which are orthogonal to laser polarization and have periods close to laser wavelengths. And also we can observe so-called hierarchical structures, which are combined HSFL and LSFL within the same area. Here are the examples of HSFL gratings formed on chalcogenites. They start to form at rather small fluences, starting from about 34 millijoules per square centimeter, and have periods about 2 or 3 times smaller than the laser radiation wavelengths. If we increase the laser fluence up to 2 times approximately, we immediately start to form the LSFL structures. And here the HSFL structures start to form at a rather moderate number of pulses, about 50 to 100. And the LSFL structures start to form at a number of pulses about 10. So they start to form like almost immediately. If we increase not the laser pulse fluence, but the number of laser pulses without increasing the fluence, we also can start to form LSFL structures, which in case of arsenic sulfide at about a number of pulses equal to 400, they start to completely overlap the HSFL structures, and we observe HSFL structures only at the edges of the crater. And in case of arsenic selenide, we observed the proper hierarchical structure when the LSFL's grating start to overlap with the HSFL structure. So here are the laser irradiation parameters, which we determined to form various lips types, as well as hierarchical structures on these two materials. And in case of amorphous silicon, we determined the regimes for formation of these structures prior to this experiment, so we skip the step with formation of single craters. We also determined the depth of the formed surface relief, and for chalcogenites, the HSFL structures were about up to 40 nanometers deep, and the LSFL structures about 100 nanometers or even slightly more. And on the next step, we need to produce large-scale areas, and we can do this by scanning the surface of the sample with a femtosecond laser beam. And in the first setup, we moved the sample by the mechanical translators, and we can apply various techniques to avoid the problem of sewing together the scan lines. We can apply like normal raster scanning, or we can irradiate it at 45 degrees angle to the surface, to the irradiated surface edge, like here. But the main problem in this setup is that the radiation speed is rather low. It's limited by the speed of mechanical translators. And so to increase the laser processing speed, we can use galvano scanner, which moves the laser beam with much higher speeds, up to 3 meters per second. And in this case, we also can use the femtosecond laser with a much higher repetition rate, and thus increase the speed of fabrication of the periodic surface structures. Here is an example of the surface periodic hierarchical structure formed on the arsenic selenide. Here it represents a combination of the ellipse with periods of about 500 nanometers, which is close to laser radiation wavelengths, and the perpendicular to it HSFL structure with period of about 200 nanometers. And this structure was formed on the surface of about 5 by 5 millimeters. Here are examples of the structures formed on amorphous silicon. We also can we can control the structures type, orientation, and the periods by varying not only the laser radiation, but we also can use some additional techniques, such as covering the sample with a thin metal layer. In this case, it was the sample with 10 nanometer aluminum cover. Well, in case of amorphous silicon, the formed structures are usually the LSFL structures type, the low special frequency lips, which start to form with pulses number of about 30 to 50, and the periods are close to laser wavelengths, as can be seen here, and the laser fluence of 0.15 joules per square centimeter is usually was used in these experiments, as it was determined that the structures are best formed at such fluences, but also increasing the fluence to higher values also results into producing of the lips, but they are much less regular. However, in case of amorphous silicon, we observed the evolution of the surface periodic structures, which was different compared to the previously shown chalcogenide materials. With increasing the number of laser pulses to about 1000, we observed the change in the orientation of the formed periodic structures. They become parallel to the laser polarization. And in this case, it is an interesting to determine the reason of such turning of the lips. And it can be attributed to the emergence of thermal electron emission from the irradiated surface. When the number of laser pulses is low, we do not observe thermal electron emission, But with increasing the number of laser pulses, we start to form the surface periodic structure with increasing the relief depth, and it results into the increase of the optical absorption due to additional scattering of laser radiation by the rough surface. And this results into the more efficient heating of this of the surface and emergence of thermal emission of electrons from the surface, which results into the change in the distribution of non-equilibrium electron concentration within the film depth and change in the modes of excited surface electromagnetic waves. We can model this using the approach proposed by John Sipe and Bonze with colleagues. This model takes into account surface roughness and electric permittivity and the incident radiation parameters and also the excited non-equilibrium electrons concentration. And this model allows to calculate so-called efficacy factor, which is the probability of emerging the lips with certain wave vectors. Here are the results of modeling for amorphous silicon. And as we can see, with the increasing of laser pulses number, the modeled structure emerges at the non-equilibrium electrons concentration lower than for the smaller pulses number, which means that with increasing pulses number, we should observe decrease in the concentration of non-equilibrium electrons at the surface. Thus, the mechanism of the turning of the lips is presented here. It includes the feedback between the formation of the surface relief and the optical properties of the irradiated film. As we form the surface relief, we increase the surface roughness and change the absorption, which results into heating of the film and changing the plasmon polariton mode, which is generated. Also, we modeled these structures formation for chalcogenides. Here are the results for arsenic selenide. And here we can see that with increasing the pulses number, we see the increase of the non-equilibrium electron concentration, which is also consistent with the increasing heating of the film, but this heating is not enough for electron thermal emission because the fluence is rather low compared to amorphous silicon. Also, we investigated the phase transformation in these materials. Here are the results for amorphous silicon. Here we can see in the irradiated film the strong signal corresponding to crystalline silicon and also a band corresponding to amorphous silicon. We can calculate the nanocrystalline phase volume fraction, which in our case resulted in about up to 67%. In case of arsenic sulfide, we didn't observe spectral changes after femtosecond irradiation, which implies no phase transformation in this material. In case of arsenic selenide, we observed the shift in the Raman spectrum maximum from 220 inverse centimeters to about 265 inverse centimeters, which can imply laser-induced structural changes in this material. Finally, the conductivity anisotropy of the irradiated amorphous silicon film After femtosecond laser irradiation, the conductivity of the amorphous film not only increases by about 3 orders of magnitude due to crystallization of the film, but also the conductivity is about 3 times greater in the direction along the laser-induced periodic surface structure ridges, which implies anisotropic distribution of the crystalline phase, which can be evaluated using the effective medium theory, which allows to calculate the nanocrystalline phase volume fraction and corresponding nanocrystalline phase conductivity, and the volume fraction is consistent with the results of Raman investigations, and the nanocrystalline phase conductivity is close to conductivity of microcrystalline silicon. In this approach, we considered the crystalline phase distribution as an array of cylinders lying in the plane of the film, elongated along the ellipse ridges. Thus, the conductivity anisotropy can be attributed to anisotropic distribution of the silicon nanocrystalline phase. But also the electric field anisotropic depolarization may affect the conductivity because of the formation of the surface anisotropic surface relief. Well, here are the conclusions of my work. The formation of various ellipse types was experimentally observed on the surfaces of amorphous silicon and chalcogenide amorphous films. The direction of the formed structures can be orthogonal or parallel to laser radiation, and it depends on it is controlled by the laser radiation. We can also form hierarchical structures consisting of overlapping structures of various types. The periods and rotations of the formed relief are in good agreement with the theoretical modeling using the SIPE-Drude approach. We observed phase transformations in amorphous silicon and arsenic selenide after femtosecond laser irradiation. However, in arsenic sulfide, we did not register laser-induced changes, structural changes. And also we observed the conductivity anisotropy for amorphous silicon when the conductivity value varies up to 3 times in different directions. Well, thank you for your attention.
Thank you. Now, please.
Please tell us more about the Galvo scanner. Which type of the Galvan scanner you use? Because you used fast Galvo scanner for working with the surface.
Unfortunately, the experiments with the Galvano scanner were not carried out by me, so I'm not very into the depths of the experimental details in this particular case.
Next question. More questions?
Have you tried using cylindrical optics in your...
Cylindrical optics? Well, in the first experiments, we tried different approaches and also cylindrical lens to produce this elongated laser beam to scan a large area. But the problem was that our beam was not quite uniform, and some parts of this elongated structure have more intensity and the other were less intense. So that didn't work quite well. But this is one of the approaches that can be used, yes.
Thank you. More No more questions. Thank you again. I have a question if Dr. Tselikov is here. No? We have no speaker. Let us go further. So next talk will be given by Dr. Pavlikov. Please. So, and please press.
Good afternoon. I would like to present a report that is entitled Laser Heating of Silicon and Germanium Nanostructures in Raman Studies. I'm representing Faculty of Physics of Moscow State University. Here is a brief outline of my report. And I would like, first of all, I would like to remind you of what happens when we investigate bulk materials using excitation lasers. For instance, helium-neon laser. Here in the left figure, you can see Raman spectra obtained for crystalline silicon at different laser intensities. And in the right figure, the plot of Raman intensity versus laser excitation intensity is presented. And as you can see, it is almost linear. And that is the most situation for most cases. But if we wish, we may apply more powerful laser radiation that may be tightly focused. And here you can see the reference of the work where Tang and Irene Herman managed to melt the crystalline silicon with the laser, argon laser, CV laser, continuous wave laser, with the wavelengths of 5142 angstroms. It had power of 1.2 watts with a spot size of 0.8 microns. And monitoring the Raman signal, they deduced that they melt crystalline silicon, and these two peaks confirmed their suggestion. In case of nanostructures, we may observe laser-induced heating applying less intense lasers. And let us consider silicon vertically aligned arrays that can be obtained by metal-assisted chemical etching. Each nanowire is approximately 10 or 20 microns long, and it has 200 nanometers in diameter. And if we study such nanostructures with conventional Raman lasers, we may notice excess heating. In the left figure, you may see the spectra obtained at different laser intensities. If we apply the lowest intensity, then we'll get the usual spectra for crystalline silicon. And if we increase the laser intensity, then the peak peak position shifts to the lower wave numbers, and at the end, at the maximum intensity, we may observe additional peak B, that is called here peak B. And this may indicate the excess heating and transformation to the metastable hexagonal silicon form. On the right, in the right picture, you can see the spectra of Stokes and anti-Stokes components that confirm the hypothesis of excess Raman heating, and the local temperature may be estimated using these measurements. Then let's go to another form of silicon nanostructures. It is porous silicon. It is also a well-known form of silicon nanostructures. It was obtained in the 50s of the previous century and attracted a lot of interest from various research groups due to the observed physical photoluminescence at room temperature. These nanostructures have different morphology. It is has a sponge-like structure, and in this case we may also observe laser-induced heating. But I should state that at that time, in the 90s of the previous century, Raman spectroscopy was widely used as a structural method to estimate the average diameter of nanowires, because electron microscopy wasn't widely used, and Raman spectroscopy was a more suitable instrument. And it appeared that many researchers confused the shift of the peak that is associated with quantum confinement effect and laser-induced effect. And due to the investigation performed by a research group, it was published in Physical Review B. It was demonstrated that the shifts of the peak for 10 reciprocal centimeters is maybe explained by the excess heating. And here in the left picture you can see the spectra obtained at different powers, and in the right picture you can see the ratio of anti-Stokes to Stokes components. And as you can see, this ratio remains the same for bulk silicon, and it increases for porous silicon if we increase the intensity. So it means that we deal with excess laser heating. And another evidence is the measurements that were performed at different wavelengths of lasers. As you know, silicon absorbs visible light in a different way in near infrared region and in ultraviolet, and in visible range it also has dependence of absorbance coefficient. So in red region the light is absorbed slightly, and in blue region it is absorbed in a different way. Let's go on, and I should say that germanium nanostructures also experience excess laser heating. And in the left picture, an electron micrograph of germanium nanowires that were grown spontaneously from gallium droplets of sizes ranging from 50 nanometers to several millimeters are presented. And in the right picture you can see the evidence of excess laser heating that was demonstrated by the Raman spectroscopy, and analyzing the line shape. It was deduced that even applying low intensities, these nanowires may experience excess heating. And semiconducting nanowires, as silicon as well as germanium nanowires, have a significant potential in thermoelectric applications, and these pictures represent their potential. And you can see that Raman spectroscopy may be applied for estimating the coefficient of thermal and electrical conductivity. Now I would like to go to the methods of germanium nanowires fabrication that were used in our study. The method number 1 is an electrochemical method. This method is based on deposition of germanium dioxide from aqueous solutions. The idea of the method is to use particles of low melting metals such as indium or gallium, which serve as growth centers for germanium nanowires. The source of germanium ions is contained in an aqueous solution, and this strategy is called electrochemical liquid-liquid-solid crystal growth, similar to vapor-liquid-solid crystal growth. In our method number 1, we used titanium foil as a substrate, and indium nanoparticles were spotted, and their density determined the density of nanowires that covered the substrate. We to vary the density, we used different weighted portions of indium, and they ranged from 1.8 to 18.4 milligrams, and the current density and the temperature of the solution, aqueous solution, are presented below. These are the typical images of samples 1, 2, and 3, and you can see that the density of nanowires changes as we vary the density of indium nanoparticles. Method number 2 is ion implantation. In our experiments, we use polished crystalline germanium wafers, and nanoporous layers were obtained by implantation of silver and copper ions with energies of 30 and 40 kevs and different ion doses. The obtained nanostructures were studied by scanning electron microscopy and Raman spectroscopy. Here are the details of the samples that are numbered 4, 5, 6, 7, 8, and 9. And I would like to draw your attention that samples 4, 5, 6 were obtained at have a smaller thickness because the acceleration energy was 30 kevs, and in case of copper ions, the thickness was greater. In this slide, you can see typical images of porous germanium layers implanted by silver and copper ions. They have, I should know that they have a similar morphology as those nanowires obtained by method number 1. Here you can see the details of our experimental setup. We used Merlin scanning electron microscope and Hariba micro-Raman spectrometer, and we used 2 excitation lasers, continuous wave lasers, helium neon laser with wavelengths of 633 nanometers and maximum power of 10 watts, and a solid state laser with a wavelength of 532 nanometers with maximum power of 25 milliwatts in the previous case. It is also 10 milliwatts. And in both cases, the minimal spot radius was 3 microns. Now we go to the experimental results. In this slide, you can see Raman spectra of sample number 1. This sample was obtained by electrochemical deposition, and it had the lowest density, so we may suppose that laser radiation interact with the substrate. And as you can see, as we increase the intensity, the line shape doesn't change. and it reminds us the typical spectra of amorphous silicon that was this spectra presented in the right figure was obtained by Manuel Cardona. So we may conclude that in this case we have no excess laser heating, but in cases of samples 2 and 3, we notice that the line shape changes as we apply more intense radiation, and it shifts towards higher wave numbers, and if we make a deconvolution, as you can see in the right picture, the contribution of crystalline germanium may be distinguished. And the black line with a sharp peak was obtained at the same intensity of 10%, but at the end of the cycle. One important detail that at first we applied the lowest intensity, then we increased it, and then we went down, and we noticed that we have irreversible changes in the form of the line shape that evidences that we have phase transition, and nanocrystalline germanium appears. Here the Stokes and anti-Stokes components of sample 3 are presented. We made the similar measurements for samples 1 and 2, but only for sample 3 we demonstrate the difference in spectra obtained with excitation laser of 532 nanometers and with helium neon lasers. Using that equation, we were able to estimate the local temperature, and as you can see, for samples 2 and 3, it increased at the beginning of our measurement cycle, and then it dropped. That may be explained that germanium nanowires are heated, and then they melt and stick together and form microcrystalline clusters that dissipate the heat efficiently. And sample number 1 is not presented in this table because there was no difference for sample 1. And now we go on, and here is the sample 4 that was obtained by ion implantation with silver ions. And as you can see, the typical this spectra is typical for amorphous germanium. So our ion bombardment amorphosized the upper layer, and we in this spectra we do not observe any presence of germanium substrate. And next, we also increased the intensity, and here the nanocrystalline peak emerged. And that is the contribution of nanocrystalline particles, not of the germanium substrate. Here are the experimental results for samples 5 and 8. Let me remind that the sample 5 was obtained with silver ions, and sample 8 with copper ions. They have the same ion dose, and if you look at the spectra, you may see the difference, especially in the right figure, a very sharp peak corresponding to the nanocrystalline phase emerges. And these dotted lines illustrating the shift and the difference in the form, in the line form. Then we go to samples 6 and 8 and 9, excuse me. And as the previous slide, these spectra were obtained at the wavelengths of 532 nanometers. And these dashed dotted lines help us to see the difference. And these results for the same samples, same pairs of samples, were obtained with a helium-neon laser. And I would like to draw your attention at the small peak, and that is not a nanocrystalline peak. It is present at all the spectra. It is attributed to germanium substrate. So in this case, in case of thin nanolayers having thickness of 30 nanometers, our radiation of helium-neon laser penetrates to the substrate, and we see the scattered signal from the substrate. And in this case, we, as you can see later, look, there's no shift, unlike in the right picture. And finally, the last pair of samples 6 and 9, also obtained at with excitation of with helium-neon laser. And in this table, the results of local temperature estimation are presented. As you can see, these estimations were made for helium-neon laser excitation. Thin layers are not heated, unlike thick layers that were obtained by copper ions implantation. They are heated at elevated temperatures, high enough to melt and crystallize germanium nanowires. And at the end, I would like provide a possible explanation for the results. If we compare crystalline silicon and crystalline germanium, especially their absorption coefficient, melting temperature, and coefficient of thermal conductivity, we may see that germanium, crystalline germanium, has a larger absorption coefficient, so it absorbs light, visible light, more efficiently, but the melting temperature is lower, and the coefficient of thermal conductivity is also less than for crystalline silicon. And that's if we consider nanostructures, coefficient of thermal conductivity drops by several orders of magnitude. That is the possible explanation for the results, and the conclusions disappeared. And heating of nanostructures occurs when irradiated with not very intense laser radiation. Heating silicon nanostructures does not lead to irreversible changes in the structure. Germanium nanostructures obtained by different methods, but having the same morphology, experience strong local heating, leading to crystallization. Thank you for your attention.
Let us thank the speaker again, and the talk is open for discussion.
Let me ask you a question. Can I ask you a question about laser-induced heating of silicon? As for me, the thermal shift of Raman band is so strong. It's about 15, if I'm not mistaken, reverse centimeters. So it's rather strange. Was it measured for, say, bulk silicon or for nanosilicon? Because in case of nanosilicon, it looked like absorption should be much higher.
I suppose you mean picture in the introduction. This one.
Yeah, yes.
These results were obtained for porous silicon.
For porous silicon.
Porous silicon.
Okay. Thank you. And what was the heating estimating? Because you can use data for thermal Raman and estimate the possible heating. How
hundreds
strong?
of degrees, hundreds, even they may excess 900, but crystalline and porous silicon has a higher melting point. So it may be heated to the high temperatures, and then it may dissipate the heat, and we will observe reversible changes. So the peak will move back.
And what about bulk silicon? Have you seen similar pronounced shifting?
Look, if we use low intensities, we do not observe any shift.
Okay.
And if in case of very huge, I should say, intensities, we may notice not only the shift, but the melting of crystalline silicon. If you estimate the intensity in this case, it will be dozens of megawatts per square centimeter.
Okay, thank you.
More questions, please.
Thank you very much for your presentation. I would like to ask you why the sample with the silver, so you have about 30 nanometers, but you see the effect of the substrate. So you see the silicon with the red laser, but you do not see in the green laser. Could you please comment why?
Green and red light has different penetration depth into germanium. That was not silicon, that was germanium. Germanium has a very large absorption coefficient, and thus it has very low penetration depth, dozens of nanometers. That's why we cannot see the interaction of laser radiation with the substrate. That was well, the border. 30 nanometers is the border. If you excess this value, then the radiation may interact with the substrate. That was the idea of taking such thin layers. And they could be fabricated only with ion implantation. Electrochemical and electrochemically deposited layers had large thickness, hundreds of nanometers.
Okay, more questions?
So again, the question about the silicon versus germanium. So what does it mean? The silicon in the silicon nanostructures, we do not observe irreversible changes. So in case of germanium, you have the structures in amorphous state, and in case of silicon, they are crystalline. And what if we have amorphous silicon nanostructures? Maybe they will be affected. What are the limits of the laser radiation intensity in Raman
in case of silicon,
yeah.
amorphous silicon? I'm not ready to give you the exact estimation, but as far as I remember, the intensity should be much higher than in case of germanium because of the difference in absorption coefficients. And it is possible also to crystallize the amorphous silicon if you apply very intense laser irradiation.
That's because in our experiments with our the laser-induced periodic surface structures on amorphous silicon, we actually at relatively intense Raman excitation we observed crystallization and like these effects.
That's the problem. So
yeah.
you have to apply At first, you have to apply low intensity excitation to confirm that you initially have an amorphous structure.
Okay, more questions, please. No more questions, please. Thank you. Speak again for So the last talk in this session will be given by Priezzhev. Please come here.
Okay, thank you. I will talk about features of the band structure in the luminescence response of two-dimensional photonic crystals with germanium and silicon nanoislands. And okay, what is our global idea? We want to create an effective source of near-infrared radiation based on silicon. Such sources are needed to combine optical and electronic components on one chip, and this will increase the speed of calculation and reduce energy consumption. Why we want to use silicon? Because silicon is the main element for creation on microelectronic chips, and we have good technology for it. And near infrared range is the most popular range in telecommunication. But we have one problem. Silicon is a non-direct bandgap material, and its radiative properties are extremely poor. And how we can solve this problem? We can use germanium and silicon nanoislands embedded in two-dimensional photonic crystals. Nanoislands are compatible with silicon technology. They can near infrared radiation, simpler formation, compactness, and have localization of charge carriers. And what is it at photonic crystal? This is a structure with periodically which refractive index periodically changes, and due to this, optical modes arise in such structure, and nanoislands interact with these modes. Due to this, we can see a magnification of luminescent signal intensity from the nanoislands. And there you can see typical band structure of photonic crystals, and we will say about photonic crystal with hexagonal lattice, and how says theory group, and this structure have C6V as a point symmetry group, and how says theory group in this structure will be 12 modes, and there we can see the real part of that projection of electric vectors in ancient mode of photonic crystals, and we can see that for some pairs at these modes, fields are okay, we can see that this structure has 4 doublet modes, and other modes is singlet. And also we can see that in this picture we can see photonic crystal band structure, emissivity photonic crystal band structure, and for some modes emissivity is vanishing, and these modes are modes with bound state in the continuum and gamma point, symmetry protected bound states, And these mods has a very high Q factor. And of course, these mods are are very interesting for us. And we need, and if you want to take a big intensity of the structure, we can use these mods. Okay, we use two series sample, and all samples were formed on thin to about 18 nanometers silicon on insulator substrate, and we grounded on this structure silicon buffer layers, 5 layers germanium on silicon nano-islands, and silicon cap layer. And after we used electron beam lithography and refractive ion etching for forming photonic crystals. In A sample, we use photonic crystal with different periods in wide range, and in B sample series, we various etching depths of holes which formed photonic crystals. For study luminescent properties, our photonic crystal, we use the micro photoluminescent spectroscopy. Usually we used standard setup when we pump and collect signal using a single objective with a normal drop. And also we can investigate a band structure of photonic crystals and how we can do it. Objective forms parallel beam, and if we add a diaphragm and this beam in center of a beam, and if we will change diaphragm diameter, we can change collecting single angle. And if we use small diaphragm and moving the diaphragm and in beam, of course, we will use a very high symmetry direction in first Brillouin zone for us photonic crystals, and we will move diaphragm. We will can get photonic crystal band structure experimentally, and also we use pump at an angle to the sample with big pump spot size just for increase photonic photoluminescent signal. First we depend the dependence of the luminescent response and the band structure of photonic crystal on its period were investigated. And it can be seen that as the photonic crystal period increase, the modes shift down in energy, and which can be explained by the resonant wavelengths. Since the modes arise due to diffraction of light on the periodic layers of holes, and the period of which increase. At the same time, the modes shift parallel to each other, almost without intersecting, and the greatest signal growth is observed when the spectral coincidence of luminescence maximum of nano-islands with photonic crystal modes. Changing the period allows we can accurately shift the photonic crystal modes. And for more accurate study of features the luminescent response, we have reduced the angle of collection of photonic crystal by quarter. By half. Due to this, we got closer to the gum point, which allowed us to narrow down the lines in the spectrum and more accurately determine the relationship to photonic crystal modes. And we observe two closely spaced narrow lines, E2 and A2, and after that we reduce the full collection angle to 6 degrees and use the spectral resolution of half an inverse centimeters. By measuring the spectrum, we determine the Q factor of the line order 260 for A2 mod, and which is a record value for such structures. The second parameter is the size of holes, or rather the ratio radius to period to lattice period, and also it calls filling factor. Here is the situation somewhat more complicated than in the case of the period. As we can see, the photonic crystal modes shift up in energy with an increase in the filling factor, which can be explained by the decreasing effective refractive index of the structure. At low filling factor, when the photonic crystal is more like a planar waveguide, and the modes are located close to each other. Then the modes are shifted up in energy and out of the radiation range and the non-islands. And the photonic crystal grid with holes essentially turns into a photonic crystal grid of pillars. And also we have at the same time there we have a technologies limit accessed with a minimum holes diameter of 200 nanometers, with smaller diameters holes of poor shape and low reproducible are obtained. Thus, it is possible to allocate such an optimal range. It's from 0.15 to 0.3. And another tool for tuning band structure is etching depth. Okay, sorry. And how we can see there is a position of modes in gamma point, and how we can see with an increase the etching depth, the modes shift upward in energy at different speed. And at lot etching depths, the branches of dispersion characteristics are of modes interesting with each other, and science, when directing a signal, we investigate the signal for each energy by angle, and as a result we get a wide spectrum. With an increase in the etching depth, the modes disperse, and there are fewer intersection, and there should be narrowing of the spectrum and an increase in the signal intensity at peak due to the better resonant interaction of nanostructures with photonic crystal modes. And here are the experimental results. As we can see, it shallow etching depths, a wide spectrum is neat. Okay, is neat observed. and which increasing etching depth at narrow and narrow line appear. But the intensity initially increases as expected and then begins to fall. The decrease in photoluminescence intensity is associated with an increased contribution of non-radiative recombination of charge carriers on the wall of holes. You can see it here. And the radiative lifetime of charge carriers shorten. That is the proportion of non-radiative recombination increase, which leads a drop to intensity of photoluminescent signal. With complete etching, the signal generally drops sharply, which may be due to removal of the lower silicon layers. The optimal etching depth is so each etch to the maximum possible depth to the nanostructure layer, but the spectrum will be wide. At the same time, there is one photonic crystal that stands out from all dependence.
1 minute.
Okay. And there we can see that these mods, this line, have a very big enhancement, and how we can see in band structure, this mod have a flat dispersion characteristic. And for this mod, because dispersion characteristic is flat, and if we group velocity are near 0 too. Okay, there we experimentally investigate spectrum with different angles, and we were close to gamma point, and we can see that Q factor for this mod is more large than for other mods. And also we have experimentally measured the band structure of the photonic crystals, and as we can see, it's perfectly coincides with the result of numerical simulation. From these measurements, we obtained experimental values of the drop velocity for different photonic crystal mods. In the vicinity of a gamma point. Here too we can see extensively consonance of experiment and theory. Okay, okay, it's all.
Thank you. Talk is open for discussion, please. Questions? If have anybody? No questions? Well, thank you, speaker, again. And I also thank all the speakers. The session is over, and in 4:30, we come back.
К этому делу не имею. Честно призналась. Это название никак. Леня
Я проверял, да, все.
So let's open the session. The first talk is presented by the group of authors, and the speaker will be Vartanyan. Yes? Okay.
Yeah.
Please.
Thank you.
Yes.
So I would like to...
20 minutes.
So I would like to tell about the possibility to use and to enhance the chemiluminescence. Chemiluminescence is a unique technique among the all optical technique because it does not need a light source. Yeah? The light is produced. The light is produced by the chemical reaction, and because of that, we do not need any other source of light. And it happens that this chemical reaction which leads to the light emission, it doesn't work for us. So, so I just say that this chemical reaction which leads to the production of light, it depends on many circumstances and other species which are present in the solution. And because of that, we can use the chemiluminescence for sensing purposes. And as a matter of fact, we can use also an analyte and a catalyst to produce the excited state of the hemiluminophore, and when this molecule comes into excited state, then it produces the photon, and which can be registered. So, yeah, I have said that, and one of the good things about this chemiluminescence is that it is basically a label-free technique. And so registration is also relatively simple, and for this reason it has a lot of applications which is listed here, so I will not repeat this. It is used in biomedical analysis and chemical analysis, and also in forensic science and many other things. So here I show the luminol, which is one of the most popular hemiluminophore, and it goes so that with, in particular, luminol is very sensitive to different oxidizer, oxygen and also the hydrogen peroxide and any form of the reactive oxygen species. So after this reaction, it this molecule transforms, goes to the excited state and goes from the excited state to the ground state, also with emission of photon. Yeah, but sorry, but you see that besides the emission of light, this molecule can also go to a ground state, also the non-radiative process. And these two processes, they compete, and because of that, the yield of the emission is relatively low. Nevertheless, it may be registered and it used, but our aim was to enhance the yield, and the natural way to enhance is to speed up the radiative process, because non-radiative processes commonly are much faster than radiative process, and the influence on the rate of radiative process will be very helpful. So there is such possibility. We know this as a Purcell effect, and I can illustrate it here, because this molecule which is shown up there, when it radiates, it has its own dipole moment. And if the media near this molecule is inhomogeneous, here I show it as this large circle, then we can induce also in this particle the dipole, which at some circumstances may be collinear and even larger than the dipole moment of the radiative dipole moment of the molecule. And this is a way to enhance the dipole moment of the transition, and because of that also the speed of radiative transition. Okay? So one of the most popular way to enhance the radiative transition is connected with metal nanoparticles. In metals we have almost 3 electrons, and besides the 1 electron excitation, they possess also so-called collective electronic excitation. In this particular way, all electrons move together in one direction. And this excitation in the 3 dimension, it is known as a plasma wave. On the surface wave form, the surface plasma polariton. And in particular, in small particle, this is a localized surface plasma. Here we can see the field distribution around the nanoparticle, which oscillates on its eigenfrequency, and this is the colors here. They demonstrate the distribution of field strength, enhanced field near this nanoparticle. So I want also to show some equations which demonstrate how large may be this enhancement. This is the formula demonstrates the ratio of a field inside the particle to the field, incident field, to the amplitude of the field incident on the particle. So you see that this is an ordinary formula very well known from electrostatics, but what is interesting here is that in the denominator we have a sum of real part of permittivity plus 2. So the plasmonic metals have at particular frequency have a real part of the permittivity equal to -2. And if the imaginary part at this particular frequency is small, then we get a rather large enhancement of a field inside, and also due to the so-called lightning rod effect, we have even large enhancement of a field outside the particle. This is the basics for the SERS, for the surface enhanced Raman scattering, but it may be also used to enhance or to speed up the radiative transition for the chemiluminescent particle. Okay? So, and this is our approach to produce these nanoparticles. Silver was chosen because of these very good material properties of it. And in the previous session, there was a lot said a lot about the production of the nanoparticles via laser ablation. Here I demonstrate also the principle, which is the same as was said before. And this is a particular setup, and we use a neodymium laser. Its first harmonic and also second harmonic may be also used to initiate the laser ablation and get the silver nanoparticles in the solution. Okay, so here I demonstrate the result of these particular things. You see these colloidal solutions of the silver nanoparticles. Also, I show here the scanning electron microscope picture of these particles of silver, these silver particles. This solution was poured on the substrate and dried, and so we can see these small silver nanoparticles. And on the left, you see the absorption spectrum of this colloidal solution, which demonstrate that indeed the nanoparticles was formed, and they have this localized surface plasmon, which is seen as an absorption band at about 400 nanometers. And you see that during the laser ablation we get more and more of these particles. This is just in seconds shown the time of laser ablation. So we can use this, but also we need to learn about the stability of this. The stability of this particle is not very high, but this is a cost of the fact that they are free from stabilizing agent. And this is important for this particular application. So we see that some precipitations took place, but nevertheless the plasmon excitation, that means the localized surface plasmon, which serves as an enhancer, it will be preserved. So, and to really enhance the emission of the luminol, I have to produce such nanoparticles that the band of the plasmonic band of which overlap with the emission band of the luminol. Yeah, contrary to what we know from the surface enhanced Raman scattering absorption spectrum of luminol does not make sense to reach, because the only thing when the light is produced, this is the emission of the light from a chemiluminescent molecule. So I have to tune my nanoparticles to the emission band of the luminol. So, and here I show the principle of experiment. We have a cover, a box, light-tight box, and there is a photon counting head, and so we use an oxidizer, thank you, so that to see what happens. And you see here that depending on the concentration of the nanoparticles, we have got almost 16-fold enhancement of the chemiluminescence. So, but this is not the only way to enhance, to produce nanoparticles. There is also a possibility to use another approach. We can use a physical vapor deposition and produce some particles on the surface. You see that silver readily produce the films, granular films, and after annealing it forms this kind of nanoparticles and with a Plasmon band which can be tuned also to the emission band of luminol. So here I show the results of experiment when we have a part of a substrate was covered with nanoparticles and some part was free of that, and you see that on those places where the nanoparticles we have an enhanced chemiluminescence. But the control in this case, when we have only the self-organized nanoparticles, then it is very low, and I suggest to use the specially prepared the periodic arrays of the nanoparticles, and to this end we have performed several calculations to see how the plasmonic band tunes when I change the height and the radius of the nanoparticles. So it may be tuned to resonance with luminol, and yeah, here's several calculation of that, and we also take into account the needs to use some additional layer to ensure the good adhesion of the silver to the substrate, and yeah. And also we need some special microfluidics channel, which is here demonstrated, so that to produce and see how the nanoparticles enhance the chemiluminescence. So this is almost everything what I want to say. So plasmonic nanoparticles, in particular silver nanoparticles, provide for considerable enhancements of luminol chemiluminescence field, and enhancement is of particular value in the biomedical application, because in luminol chemiluminescence is rather large in basic solution with large pH values, but in neutral and condition and low pH value relevant for biomedical applications, it is rather low and it should be enhanced. So that's all. Thank you.
Thank you. Question?
Did you consider gold nanoparticles for your?
Yeah, sure. Gold is very attractive, but the gold sphere has a resonance in water about 550 nanometers resonance. So there is no way to shift it to the blue. There is a lot of possibilities to shift it to the red, far into the red, but not to the blue, because of that silver. And silver is a little bit too in the blue, so I can tune the resonance, plasmonic resonance, a little bit to the red and make a good overlap between the spectra. Yeah, but of course, gold would be better for such applications.
You see a lot of lines in absorption of silver nanoparticles. What is the reason for that?
A lot of lines?
Absorption.
I have just demonstrated different spectra for different form of nanoparticle.
It is resonances in silver nanoparticles.
Yeah, this is all resonances of silver, but with different shape.
Plasmonic resonances.
Plasmonic.
Resonances.
No. This is plasmon resonance, in particular in silver nanoparticle of particular shape, and I have shown here the difference in the absorption spectrum for the particle of different shape.
Any questions? I have one question of semantic sense. According to the classical definition, the luminescence is the emission above the thermal emission. And you told that you have much more losses for non-radiative processes than radiative. But it doesn't mean that all non-radiative processes gives the heat radiation. But finally, yes.
Temperature rise.
Yes, and what is the ratio of the thermal radiation and luminescence in your case? Losses, I understand, but radiation.
These losses lead to increase of the temperature of the solution, and thermal radiation will
Yes,
be...
it might be spent for emission, or it might be spent for chemical reactions, and so on.
Non-radiative losses, I think that it's...
Everything to radiation, no?
No, non-radiation means non-radiation.
This is semantic question. Yeah. Okay. Please, more questions. Thank you. Please switch on next presentation. Please start the presentation. The next report is by Manshina from St. Petersburg also. Yes.
Thank you so much. Dear colleagues, my name is Alina Manshina from St. Petersburg State University Institute of Chemistry, and I will talk about laser synthesis for SERS, for surface-enhanced Raman spectroscopy. And I'll start with the approach, laser-induced deposition or laser synthesis, that was developed in my group. And I want to focus your attention on simplicity of this process. First of all, we prepare some liquid, this yellow liquid. After that, take very small amount and put it into a rather small cuvette. Here you are. After that, we cover it with substrate. Any substrate, for example, microscope cover glass. You can see it here. This is our laser. Everyone knows helium-cadmium laser, CV. Very simple optical system, or no optical system at all, just mirrors. Here you can see luminescence of yellow liquid. We really have a laser beam. So we put our cuvette under the laser beam, and look, laser beam is unfocused. Then we have some time for coffee. And here you can see that in laser affected area we have some dark spot. So this is the process of laser-induced deposition. And on the next slide, I want to show you more about the scheme of this process. The main participants of the process are liquid. This is source of metal. Substrate, this is surface to be covered, functionalized by the metal. And we have laser beam as initiator of process, and laser beam also provides for localization of the process on the surface of the substrate. And you can see here that geometry of deposition can be different. It depends on transparency of the substrate. For transparent, for laser beam substrate, we can put substrate on the top of liquid, and if substrate is non-transparent, it's on bottom.
Now I want to tell you about this secret liquid. Also, I want to focus your attention that composition of solution is very simple. We use some precursor. It can be organometallic complexes or metal organic salts. And we use solvent. Any solvent in which precursor is stable, is soluble, and solvent should be transparent for laser radiation. That's all. And here you can see the result of laser-induced deposition from different precursors on surface of microscope cover glass. Here you also see the structure of precursors that we used, and so we succeeded in deposition of cobalt structures, ruthenium, and different metals like platinum, silver, gold, and combinations, bimetal and even 3-metal nanostructures. And here you can see also the formula of precursors that are used in our experiments. It's clear that cobalt and ruthenium precursors and silver are very useful for electrochemistry, but I'm going to tell about CERS. And as previous speaker explained us, silver is the best candidate for plasmonic resonance. That is why I will talk in my report about silver mainly. So again, the scheme, you can see the same scheme, and as precursor here we used silver benzoate. This is organic salt, and structure you can see here. This is absorption spectra of solution of silver benzoate in methanol, and we used laser with wavelength 266 nanometers. It fits to some absorption band. As a result of laser deposition, we obtained nanoparticles. This is continuous coating of the substrate. And later this substrate was used for measurement of analyte that is important for biomedicine. These experiments were carried out by our colleagues from Moscow. So we measured solutions of beta amyloid. This is peptide. This is a biomarker of Alzheimer's disease, and at high concentration of these beta amyloid, some aggregation of amyloid to fibrils take place that results to stimulation of this Alzheimer's disease. That is why modern urgent task is detection of beta amyloid and identification of aggregates. So on the left, you can see two CERS spectra measured from our substrate. This is a spectra of original beta amyloid, red line, and aggregate of this beta amyloid. I want to focus your attention that the specific characteristics peaks typical for beta amyloid and aggregate are different. That is why it's possible to distinguish between aggregates and beta amyloid itself in analyte. And here you can see the parameters of CERS that we obtained. Enhancement factor not too high, 10 to 5, but rather low detection limit, 10 to minus 11. The manuscript was just accepted for publication. Look, here I show you the same precursor, the same experimental scheme, but another solvent. Here is water, and another laser wavelength, 448, sorry. And as a result of the same process in another solvent, we obtained absolutely different structures. These are silver fibers. And here you can see fibers obtained at different laser irradiation time. I was surprised to see that at small laser irradiation time, we have already long fibers, long winding fibers. I suppose to see shorter fibers or smaller particles, something else, but we had long fibers already at the first stage of the process. That is why we carried out experiments in a second regime. And here, look, you can see some fiber-like structures. They are branched organic nanostructures, and we called it protofibers. Then individual silver clusters are formed on these protofibers. And increasing of laser irradiation time results in growth and ordering of these silver clusters. Thus, we obtain silver nanowires. Here you can see the results of Sears experiment for these nanowires. Here you can see absorption spectra of nanowires, and obviously it is rather wide. Experiments on Sears for methanol blue and rhodamine 6G demonstrated rather high enhancement factor and rather low detection limit. And here you can see the mapping of enhancement factor calculated for different wavelengths, 532 and 632. And we can see that the places with high enhancement factor is different, but amount of these places is the same. So we have more or less homogeneous increasing of intensity, and this is observed at different wavelength of laser radiation. So, in such a way, we demonstrated possibility of creation of nanofibers with very simple technique. We didn't use any surfactants, capping agents, catalyzers, any templates. And these fibers were obtained as a result of single-step process, and fibers are formed directly on the substrate surface. And as I showed you on previous slide, as a first step of formation of these nanofibers, we observed organic fibers. So, organic fibers, the origin of these organic fibers are benzoate anion. It means that ligand of precursor plays an important role. That is why I show you examples of laser-induced deposition for different structures as precursors. These are homemade organometallic precursors. Formula you can see on the top. It consists of silver and gold, and as a result of laser irradiation of solution of these precursors, we obtained nanoparticles, flakes, B structure, and flowers, C, figure C. In accordance to our investigations, we found that nanoparticles consist of carbon, and in this carbon, a lot of bimetal gold-silver nanoparticles were found. As carbon, we have amorphous hydrogenated carbon. But for flakes and flowers, the nature of carbonaceous matrix is different. It was found to be crystalline hydrogenated carbon of sp2 hybridization, and again metal nanoparticles, bimetal nanoparticles inside of these structures. Okay. Here there is the explanation why and how we obtain such structures, but here I want to skip the slide. We can come to it later. Here I present a demonstration of functionality of nanoparticles, flakes and flowers as Sears substrates, and as analyte, monobutyl trichloride was used. This is a rather dangerous organotin compound. And it's important that any structure presented here demonstrate rather good Sears efficiency. But everybody knows that Sears is provided by metal nanoparticles, and this is true. And again, here you can see the Sears activity presented for anthracene as analyte. And we see a really good reporting ability for impurity detection for these hybrid nanoparticles. But we also have carbonaceous phase in other hybrid materials. And here we demonstrated the impact of this carbonaceous matrix for efficiency of Sears. As a test substance, we used a drop of my blood in water. The concentration was very small, and we didn't succeed in measuring of Sears spectra from the surface of these hybrid nanoparticles. But increasing of immersion time of substrate into the analyte allowed to obtain some signal from blood components, and increasing of this immersion time allowed to get good Sears signal from a very low concentrated solution. Maybe I will skip it also. And as a conclusion, I want to tell you that laser-induced deposition can be realized in any laboratory with very simple metal precursors and very simple laser source. Both metal and ligand in precursor are important for laser-induced deposition. That is why it can be controlled composition, structure, morphology, and functionality of structures that you obtain. And this is very important that synthesis takes place directly on the surface of the substrate. It provides very good adhesion of material to the substrate. And as a result, it's possible to give a function to a structure of to surface of any architecture for Sears or electrochemical applications. And finally, I want to thank my colleagues and funding for support our research. Thank you so much.
From the previous slide, I conclude that it's useful for young terrorists.
Oh no, this is about fixing the aim of research.
Because everybody can do it. You explained this very simple technology. You made it.
Yes.
Okay. This Joe. Yeah?
It's a beautiful woman, that's only.
Here, they are familiar. I thought that.
Yes. Yes.
Yes, please.
I'd like to ask you, first of all, is it really is it really the best substrate is like brush? Like brush, because in this case you have the many possibility for deposition. Is it true? Because you demonstrated a different.
Do you mean this one?
Not only when you fibers. And this, and what is the best for your purposes?
Okay, thank you for the question.
I'm not finished. And first of all, it is very impressive, your movie. It is very nice, included in your talk. It is very nice.
Thank you. This is our home video, yes. At the moment, it seems to me that fibers, nanofibers are the best. Because we have different sites for plasmon resonance. Different sizes of elements, different gaps between metal surfaces for hot spots, and so on. Yes.
So your opinion that it is the best?
From the list of our substrates, yes.
Yeah. My question is concerned with the last part of your talk when you detect blood cells. The blood cells has many features. Can you distinguish some disease of blood or some specific features?
Thank you for the question. In reality, it was experiment, I want to say, just for fun. Because we really had only sample of my blood, not much. And as a next sample, we mixed blood with anthracene. I want to say that we can distinguish blood and anthracene in water. But studying of and detecting of diseases should be the next step.
This is a hard question, because all diseases are from the nerves.
Yes, but
except one. Yeah.
But this is about Alzheimer's disease, and I showed that we can distinguish.
Thank you. More questions, please.
Вот, просто, может быть, необычный вопрос, практический. Вот если, например, взять среду с вашими наночастицами, да, и воздействовать во время плазмонного резонанса, не будет меняться показатель преломления среды во время плазмонного резонанса? Вы так, не думали над этим?
Допустим, что?
Допустим, вы взяли среду, поместили туда свои частицы и воздействовали излучением каким-то, лазером, например, зеленым или там синим, где плазмонный резонанс, а другим лазером анализируете показатель преломления среды, будет меняться или нет?
В связи с чем вопрос?
Просто
на развитие это.
Просто как бы, интересные вещи на стыке рождаются, может быть. Вот. Это просто мой интерес. Как бы.
Может быть, да. Спасибо.
Все?
Yes. It could be.
The answer is okay. Yeah. Пожалуйста, еще вопрос. Если нет, спасибо. Значит, я Александру передаю микрофон, мы почти вовремя идем, 5 минут всего.
My name is Alexander Pavlikov. I will continue the session, and I would like to invite Daria Nazarovskaya to make her presentation. Daria, you have 15 minutes.
Good afternoon. My name is Daria Nazarovskaya. I'm from Lomonosov Moscow State University, the Department of Medical Physics. It's such a pleasure to be there. I would love to thank the program committee of this conference for the invitation. And let me present you recent results of our research that has been made in the collaboration with Gamaleya Institute about CERS active silicon, composite silicon nanostructures for bacterial identification and antibiotic susceptibility testing. To begin with, bacterial infections is a topic that gains more and more attention today because it affects millions of lives. What is more, there is a growing number of antibiotic-resistant bacteria. So now, many serious diseases such as tuberculosis or gonorrhea or sepsis cannot be treated effectively since they are induced by drug-resistant bacteria. So in these situations, time is really precious, so we need to detect bacteria and to find appropriate antibiotic as soon as possible. Culturing-based methods and advanced techniques such as PCR reactions or immunoferment analysis and so on contribute to the current state of bacterial diagnostics in clinics today. Each of these methods has its own pros and cons, but in overall they have very important limitations such as they need really specific laboratory equipment and they are time consuming. Different alternatives for rapid and in-field bacterial diagnostics are developing. Raman spectroscopy holds a great promise because it offers non-invasive, label-free and rapid diagnostics of bacteria. It is based on the phenomena of inelastic scattering that is a result of interaction between light and the matter, and as a result the light frequency changes and we obtain a spectrum which is also called molecular fingerprint because it is very unique for every molecule. However, intrinsically Raman signal is weak, so different methods are developing for its enhancement. So surface enhanced Raman spectroscopy is one of such methods. It enables us to obtain Raman signal, increase in Raman signal up to 1 billion times. Surface enhanced Raman spectroscopy has been used for bacterial detection for a while, but there is still a problem of reproducibility of CERS substrates or homogeneity of their surface. So in our study, we offer to use porous silicon nanovirus decorated with gold and silver because they have some advantages. We developed a method which is highly reproducible and also their surface is very homogeneous. We use metal-assisted chemical etching method. It is a very simple technique and cost-effective. It is a two-step process by which we can obtain nanowire-like structures through the deposition of metal nanoparticles. So on this slide, you can see the structure of our obtained substrate. We obtained nanowires which were very vertically aligned, and then they were decorated with Okay. They were decorated with noble metals that formed dendrite-like structures, which in turn formed pores with sizes about microns, which is very good for bacteria that has sizes like several microns. For our experiment, we used Listeria bacteria. It's a bacteria that can cause listeriosis. For SERS measurements, we took this bacteria in suspension. For this suspension, a special cell was created, which included metal base and fluorine calcium optical window. On this slide, you can see the situation after adsorption of bacteria onto the surface of our nanovirus. As you can see, bacteria tend to fill the spores that were formed by dendrites, which would lead to better Raman signal enhancement. So on this slide, you can see SERS spectrum of our bacteria adsorbed on our substrate, and you can see some lines that then are correlated with Raman frequencies of gram-positive bacteria, Listeria, and in comparison to just Raman measurement, you can see that substrate without SERS enhancers isn't enough to identify the bacteria. Then we also have concentration dependency, and we can actually obtain very good enhancement up to the concentration of 6.2 and 10 in the power of 6 bacterial colonies per milliliter. Eventually, we performed the antibiotic susceptibility test of Listeria, and we compared our developed SERS method to traditional disk diffusion method. In fact, using our substrate, it's enough. One hour is enough to determine the sensitivity of bacteria to one or another antibiotics, while disk diffusion method requires about 30 hours, because first you need to let bacteria grow into a monolayer, and then it should be incubated with an antibiotic again overnight. In conclusion, I would say that in our work we developed a method, metal-assisted chemical etching method for the production of substrate for surface-enhanced Raman spectroscopy. Then we performed these SERS measurements using Listeria as a model object. Also, we carried out antibiotic susceptibility test, and these results have very good potential. Very good potential. So thank you for your kind attention.
Thank you, Daria. I suggest asking questions.
Quite general question. You are talking about the different type of scattering, also include the Stokes and anti-Stokes scattering. What do you think, or maybe you know, what is the difference in the ratio of anti-stocks to stocks in volume and on the surface. Do you know about something?
Thank you for your question. I think I will get to know about it.
Now my question is, the reason is the following. If you have the molecule on the surface, it may be, if the quantum is not too much vibrational quantum, that maybe the phonons from lattice can be transferred to vibration to molecules. So in this case, the anti-stocks will be enhanced, in this case, compared to the free space. Doesn't matter, liquids or gas, so on. Do you know something about this?
Well, thank you for your comment. I think I will get to know something about it. Thank you.
Any more questions? Nobody wants to ask another question. So we would like to thank you, Daria, once more. Thank you very much. And we go further. The next report is entitled Stimulated Raman Scattering in the Ultrasound Wave Field High Conversion Efficiency. And I would like to ask you, may you introduce yourself?
Yes.
Is it possible?
I'm Anna Priezzhev from Lebedev Physical Institute, Optical Department. Stimulated Raman scattering from its discovery in 1962 till now is an object of intense experimental and theoretical studies. The first reason of it is a number of practical applications, such as Raman spectroscopy, which is used in many different fields, frequency converters, Raman microscopy, Raman imaging, dynamic holography and image processing, and many others. And in all these applications, the key problem is stimulated Raman scattering efficiency. There are few ways to increase this efficiency of the scattering. It's optimization of exciting light characteristics and structures, using structures with photonic band gaps, for instance, nanostructures, local field effect, and distributed feedback, which is also a very serious method. And in our work, we present the experimental investigations of ultrasound effect on the stimulated Raman scattering efficiency. We used two experimental setups with different geometry. In the first setup, we focused exciting light from above to the open surface of the liquid. And in the second geometry, we focused exciting light through the side wall of the cell. In all these, in both geometries, the cell with sample liquid was put into the ultrasonic bath with maximum power 200 watts and frequency 40 kilohertz. And for excitation, we used second harmonic of picosecond neodymium YAG laser. In the first scheme, we put our focusing lens on the moving platform, which helped us to change the position of focal waist of the exciting beam. That is, we could change the distance of this focal waist from the surface of the liquid. It's well known that intensity of stimulated scattering, different types of stimulated scattering, increases when the focal waist of exciting light is near the surface of the liquid. We observed this effect in our case. In the first case, when we focused exciting light on the surface of the Raman liquid. Here we can see the spectrum for different focal waist position for two exciting energies. And we see that for on the left picture, it was near the threshold, and on the right, it is larger, and we see here effect of ultrasound. This was in water, and we observed the effect of ultrasound action also in heavy water and in ethanol. I didn't say that we took rather usual liquids for our first experiments. Maybe not optimum by its Raman gain. And we see that for heavy water, the stimulated Raman scattering intensity increase by observed increase by more than 2 times. And for ethanol, for first stocks, increases by 15 times, and for second stocks, we also observed it, it's by 4 times. Here we can see energy dependence of stimulated Raman scattering intensity for different power of ultrasound. In these experiments, we took optimum distance of focal waist from the free surface of the liquid. It was 1.5 millimeters below the surface. And we also observed this effect when the exciting light was focused through the wall of the cell. In this case, we could register not only backward scattering, like in first case, but also in forward and backward direction. And here we also can see very significant increasing of stimulated Raman scattering intensity. It's more than order of magnitude. Which are reasons of this effect? Under the action of ultrasound in liquids, randomly distributed phase inhomogeneities arise. The reason of these reasons may be following: acoustic currents of vertex flows, then cavitation, which means formation and collapse of small bubbles in liquid. and also shock waves which arise during cavitation. And these randomly distributed phase inhomogeneities lead to the appearance of randomly distributed feedback, which results in the increasing of stimulated Raman scattering efficiency. That is, decreasing of the threshold of this effect and increasing of this conversion efficiency from exciting light to the scattering. So we observed stimulated Raman scattering efficiency increasing under the action of ultrasound. We observed it for excitation by picosecond pulses, and if ultrasound was turned on simultaneously with excitation light, we observed this effect. The effect was registered both for forward and backward scattering, and also it was registered for higher order components. And we think that this effect can be observed also for another types of stimulated scattering, and as well as for luminescence.
Thank you very much. Thank you very much. I suggest asking questions.
You cited the work by Akhmanov and Lekhov 50 years ago. Was it what is on the liquids or on the liquid crystals?
Liquids.
Simply liquids. Yeah?
Only
because
in these experiments we used only liquids.
What kind of liquids?
I didn't say. We used for first experiments rather simple liquids: water, heavy water, and ethanol. And why? Because they are usual Raman liquids with a very well-known spectrum, and we wanted to see this effect for first for very usual liquids.
You don't know how simple?
You see, it's this also only beginning. It was first experiments, and I think that, of course, we'll try to make experiments with another samples, and maybe not only with liquids, but maybe with another. And of course, it's interesting to see this effect for another types of stimulated scattering.
What's the difference in this sense between the simple normal water and heavy water?
Heavy water.
Slide back.
What's the reason of different action on it? Difference.
May you show the slide?
Why?
With
The reason of this difference between why it maybe not maybe this phase in homogeneities are different and flows in the different. So the action of this randomly distributed feedback is a little different.
Thank you. Please.
Yeah, I think we will expect that your ultrasonic action can change structure of your sample.
Not structure, but structure of phase distribution.
So you cannot analyze native sample. You change structure of your sample during your analysis.
Changed only under the action of ultrasound. The liquid was the same, and we turned off and turned on ultrasound. So the structure changed only under ultrasound.
The ultrasound was not powerful enough to destroy.
No, not too powerful.
It is difficult. It's not a solid
usual
sample.
ultrasound path.
There was another question.
Do you register a difference between the increase in simulated Raman scattering efficiency in backward direction and in forward direction? Was there any anisotropy in efficiency increase of stimulated Raman scattering?
No, it was approximately the same, increasing.
Mm-hmm. Thank you. And we thank you very much once more. We should go further. And I invite to make a presentation entitled Symmetric CC Stretching Mode as a universal characteristic of lengths of polymethylene chains, experimental and DFT study. Please introduce yourself. It's okay.
Good day, dear colleagues. My report will be about symmetric CC stretch mode as universal characteristic of length of polymethylene chains, experimental and DFT study. To be brief, I will speak CC mode. Somewhat about motivation of our task. Many matter. There are many matter whose molecule contain polymethylene chains. The physical properties of such matter depends on both lengths and number of change in this molecule. The LAM mode is well-known Raman marker of chain length. It is mode. This is mode. It's easier to detect in the solids. So first of all, solids alkanes. But if we work with liquids, we must avoid two modes. The LAM mode, which belong to vibration of planar molecules, and DLAM mode, which belong vibration on non-planar mode. The DLAM mode is mask LAM mode, and LAM mode is has low intensity. It's very difficult. It absorbs in liquids. For example, this Raman spectra of alkanols and of saturated fatty acid. We must see that LAM mode absorbs only for one alkanols absorbed only for very short matter or long solid matter for many matters with an higher than 7 is absent. For saturated fatty acid, we made the LAM mode only for solid. For liquids, LAM and the LAM part are not considered traditionally. Thus, we need other marker to detect chain lengths for many polymethyl chain compounds. The Raman spectrum polymethylene compounds contain C-symmetric stretch mode. It may be surprised that this mode are studied only for normal alkane. For other compounds, this mode is poor study. Our aim is to consider a potential of symmetric C-stretch mode as marker of the molecular change length. This is symmetric stretching mode. It is observed in the middle spectrum region from 1,100 to 1,150 centimeter inverse. It is easy to detect both solid and liquids. But the behavior of this mode very dramatic for different matter. For example, wavelength is decrease with wavelength. For one alkanol and saturated fatty acid increase. We are find the simple function to determine change length for one alkanol and saturated acid. But we are find out for one alkanol and saturated fatty acid, the CC mode is influenced by intermolecular interaction. The most impressive result we obtained for saturated fatty acid. It is experimental and DFT data and classical consideration for normal alkanes. It is not matter how we will consideration the behavior of the wave number for this matter. We obtained the same results, but if you begin considerate the behavior symmetric CC mode for saturated acid as isolate molecules, we will make confusing situation. It is dependent from wave number on and for isolate molecules. It is contradict experimental results, but if you we construction two molecules or dimers, we obtain the good coincidence CC mode from CC mode from experimental и DFT calculated wave number. But the very interesting behavior of this CCC stretching mode for matter whose molecule contain two chains. We may see splitting if molecule contain two chains in which if which two chains non-equivalent from length. And in the spectrum we may see splitting. Each component of this splitting depend of chain length of planar segment. But for two chain molecules is possible two conformation. First conformation, it is specific segment with non-equivalent chain lengths, but there are other conformation when is two chains that is equivalent in its length. In this case, we will observe in Raman spectrum single bonds. Thus, we may differ from different conformation by using CC mode. Conclusion. Monitoring of this symmetric CCC strange mode allow to quantify the length molecule for substance whose molecules contain a single polymetallic chains. The wave number of the CC symmetric strange mode for such substance depends on chain length of molecules and the mass of the molecular end groups. The presence of two chains in the molecule which are not equivalent in the chemical composition and length leads to splitting of the band corresponding the CCM stretched mode into two molecular components.
I suggest asking questions.
Can you explain? This is the experimental result. Yes, I have an idea. If you have the molecule, say, with 10 atoms or more, if 10, that you have the more or less more than 20 degrees of freedom of this molecule. What reason that one mode is so strongly controlled than another? 3n minus 5 or 3n minus 6, this is a number of types of vibrations. And you observe, you fix only one. Why the another 30 so strongly controlled by this? What, have you an idea?
Yes, of course, the spectrum of polyethylene compounds contain many bonds. But their bonds correspond to 4 planar molecules. Their bond correspond to non-planar molecules.
Only one.
Only one. It is only 3.
3n minus 5 or 3n minus 6, if symmetric or non-symmetric. So,
one. Azimuth, it is not small, what differ from chain's length. Only free mode depends from chain length.
Thank you. Any more questions? Is it possible to show on that your animation which mode is associated with that position that you marked with green arrow? Animation with a chain? You had an animation. Oh, this one. Is it possible to point which vibration is sensitive and is marked by a green arrow? No? It is difficult to make.
Oh, green? Yes. This?
Yeah.
This. Okay. It is.
In the middle or?
2CS6. It is correspond by wave numbers.
And is it in the middle of the chain or at the end? The vibration, or which complex?
Okay. It is not other picture. The one.
In the center, no?
That is from one shade is very intensity for one mode. Other is will be active. Will be intensity for other mode.
So
it is not shown.
Am I true that it is in the center of this chain, the vibration in the center? No?
Yes.
Oh, okay. Thank you. Thank you once more. And we shall proceed, and I invite another participant with a presentation that is entitled Raman Spectroscopy as an effective tool for evaluating the iodine values and carotenoid content in vegetable oils. Please introduce yourself.
Good afternoon, dear colleagues and participants. My name is Sergey Kuznetsov. I'm from Prokhorov General Physics Institute, Moscow. As you all know, vegetable oils are very healthy and they're good for human organism. They contain a lot of different vitamins. They contain carotenoids, which are very good for human health, etc. Vegetable oils are used in many industries, such as food industry mostly, cosmetics, and pharmacy. The features of vegetable oils, they depend mostly on their structure and on their fatty acid content. So for human care, for human health, it is important to control the content of fatty acids in oils and control the carotenoid content. It may be possible to do with many different techniques. The standard technique is a chemical technique called titration. Here in this study, we show that Raman spectroscopy can also be a good technique to control the content of unsaturated fatty acids, and it can be much more profitable than the titration. And the purpose of this work is to establish the dependence of Raman spectra of oils on the content of unsaturated fatty acids and to evaluate the applicability of Raman spectroscopy in detection of content of carotenoids. vegetable oils consist mostly of triglycerides of carbonic acids, carboxylic acid, sorry. It's just an example. And acids can be divided into two groups, saturated and unsaturated. Saturated acids contain only single carbon bonds, and unsaturated acids contain 1, 2, 3, 4, or 5 double carbon bonds. Unsaturated acids, they are responsible for the quality of oils, responsible for their expiry dates, their heat and oxidation sensitivity, sorry. So they are very interesting to study, and the main characteristic of oil that depends on their content is iodine value. Iodine value is the mass of iodine that can join 100 grams of oil. So in this study, in this work, we studied unsaturated fatty acids in different oils. We studied by two different methods. The first method is Raman spectroscopy. We used Raman microscope Centera tube, and we used two different laser excitations, 532 green laser and 785 red laser. And the additional method is titration. This method helped us to evaluate the iodine numbers of our oils, which we had quite a lot of, 39 various vegetable oils. These are just the samples of them. And let's move on to the results. On this slide, you can see the samples of Raman spectra of several vegetable oils. They all are normalized to the intensity of this Raman band. Here we can see that there are two bands marked with blue. Their intensity increases with increasing the content of unsaturated acids, which is also proportional to the iodine number. And these spectra are ranged from low iodine number to higher iodine number. So theoretically and practically, we can use the intensity of these two lines, two bands, to evaluate the iodine number of oils by Raman spectra, from Raman spectra. These Raman spectra are shown for the green excitation laser, 532 nanometers. And here we can see two more bands marked with green. They are associated with vibrations of carotenoids in oils. Therefore, in our samples, we can detect the presence of carotenoids in oils with a content less than 1.4 milligram per kilogram. If we look at the spectra, the same oils recorded with the red laser, 785, we don't see the bands of carotenoids here, but we see again the two bands that correspond to the unsaturated fatty acid. So we can use them to measure their content and iodine number. For all the 39 fatty acids, we built the dependence of their intensity. It was a peak intensity of these two bands for green laser to the left and for red laser to the right. And we can see that in the range of iodine values starting from 50 or 60 and more, we can fit these dependencies of intensity to the iodine number with the line, with the sorry, with the linear functions. Here I show the linear functions for our results, and this work is still on. It needs a lot of, not a lot of, more points to make these equations more accurate and to get rid of this quite large spread of the points. But now we can, with these relations, we can estimate the iodine value of vegetable oils from their Raman spectra using two bands. So the conclusions are on the screen. It's about what I said, that we can use two lines, that and that we show the dependence of intensity of these lines versus oil iodine number is linear for this range of iodine number, and also we show in our work that with using the excitation wavelength of 532 nanometers, we can carry out additional diagnostics of carotenoid contents in our oils. That's it. Thank you.
Thank you very much. Any question?
One question, simple. What does it mean? 60 J2 per 100 grams of oil. What's the number of agents?
Yes, these numbers, these are the iodine.
60 gram iodine per 100 gram.
Yeah, yes.
Is it realistic?
It is, yes, it is realistic because
So the oil contains so much
it can contain, because oils consist of among others, they consist of unsaturated fatty acids, and when it
I mean the number of molecules containing one atom of iodine. What does it mean? 60 plus 100 grams.
60 grams of iodine.
I understand what does it mean 100 grams, but I don't understand what does it mean 60.
It means that when you mix a special blend with putting in 100 grams of oil.
This is a number of atoms.
No, it's mass of oil. You mix 100 grams of oil with ethanol as some more mixtures, and then you add 60 grams of iodine.
So you do it intentionally. Does oil contain iodine?
No. Oil doesn't contain iodine. We do it to see. Let me explain. When you
so you make a mixture.
Yes, we make a mixture, and in this mixture, it's a standard chemical experiment, because when the iodine is added, the double bonds are broken. They add the iodine atoms very strongly, and
they replace.
Yes, the number of iodine atoms is equal to the number of is proportional to the number of double bonds, and therefore it is proportional to the content of unsaturated fatty acids. So if the oil contains mostly of unsaturated fatty acids, they can take and they can integrate a lot of much iodine.
So you have proposed a method to determine the concentration of fatty acids. Am I right?
No. This method is standard. It is known a lot of years ago. Yes, and chemistry operates with this for a long time. Here I show that we can. This chemical method is very long, and it includes a lot of poisonous matters, and it costs very much. And here I show that we can use Raman spectroscopy for evaluation, not for very accurate number. For just evaluation, the iodine number is instead of chemical, because here we put our oil in the spectrometer. 5 minutes later, we have the oil number.
Now it's clear. Thank you. Any more questions?
I have just little one question. One, do you not use palm oil?
Yeah, it's a good question. Thank you. We decided, and we want to use the palm oil, but it has a very low iodine value, and for these iodine values, the oils are butters. They are quite solid, and they can give some contradictory results with the dependencies that I showed. So maybe we should examine them as an additional block of oils, and then maybe compare them. Yes. We have coconut oil here, but I can show you that this point is for coconut oil. Yes, but we are not sure about the content of this very coconut oil, because for all the other oils we had documents with their content, and for coconut and 2 cocoa butters here we don't have documents, so they maybe have some more acids or something in their content. But this work is still going on, so thank you.
Thank you. Thank you once more, and we shall proceed. And we have yet another report, and our section is extraordinary, and because it is the second report that will be made in Russian. Do you have any objections? In the morning we have listened one report in Russian. The presentation will be in English, and the report will be made in Russian. So I would like to invite our participant. Please.
Добрый день, я представляю Московский институт электронной техники, город Зеленоград, Москва-Зеленоград. Вот. И также в ГУП экран Самара, ну, то есть и то, и другое. Вот. Эта работа велась как бы в 2 местах. Ну, я представляю, ну, сейчас от экрана, потому что основные работы практически были на экране выполнены, а измерительные работы в МИЭСе. Эта работа возникла из практических соображений, потому что сейчас, ну вот, например, МИЭТ, Московский институт электронной техники, занимается тем, что создает новые приборы, гироскопы, измерители скорости. Вот, ну, и вот гироскопы, которые создаются на волноводах, там, ну, мотаются километры световода, чтобы сделать этот гироскоп. Вот. Ну, а чем отличается, ну, например, электроника от оптики, от оптоэлектроники? Оптические материалы позволяют получать резонаторы с большой добротностью. Но добротность, например, резонатора оптического ну, может составлять 10-12 степени. Но добротность, ну, допустим, обычной электроники там, ну, 100. Ну, максимум в СВЧ, ну, 10 тысяч. Вот. Но мы видим, что на порядке добротность в оптике, ну, выше, чем в электронике. Поэтому, в общем, электроники заинтересовались оптикой и хотят ее применить, ну, в своих как бы применениях, ну, в своих задачах. Вот. Ну, поэтому мы начали создавать слои для оптических волноводов. Ну вот, в частности, очень перспективный слой для оптических волноводов – это двуокись титана. Вот. Двуокись титана научились вокруг не экран получать. Вот. Большая проблема была с травлением, то есть травить сначала не умели, там какие-то, ну, очень хитрости такие, технологические большие были. Ну, мы с ребятами отлаживали этот процесс, но в течение 3 лет. Ну, научились травить волноводы. Вот. А после того, как волноводы научились травить, ну, нужно было, значит, их тестировать. Сделали волноводный слой, какие там потери? Ну, непонятно, надо было измерить. То есть, если поперек, например, просвечивать пленку волноводную, там ничего не увидишь. А если вдоль ее просветить, вогнать, например, в нее вот с помощью призмы туда излучение, вот, можно уже нужно что-то померить. Вот. Ну, и когда, ну, светим на призму, там возникает призма, во-первых, должна быть с показателем преломления намного, ну, по крайней мере, ну, хотя бы немножко больше, чем показатель преломления волноводного слоя. Вот. И у двуокиси титана показатель преломления где-то порядка 2,6. Вот. Если даже применить алмаз, алмазную призму сделать, ну, не дотянет. То есть у алмаза 2,4 показатель преломления. А нам надо, по крайней мере, ну 2,6 сделать. Вот. Поэтому нашли такой материал, ну, в фирме Русген, который занимается драгоценными камнями. Ну, нашли этот, значит, драгоценный камень, значит, просветили его, распилили, сделали из него, из этого камня 2 призмы. Вот, и, то есть, как бы, пришлось вручную, потому что из-за эмбарго мы призмы такие рутиловые купить не могли просто. Вот, сделали сами. Вот эту призму, вот так, туда. Сейчас. Вот. Ну, это там получается как бы исчезающее оптическое поле, которое проникает в волноводный слой, и если выполняются условия скорости распространения волны в призме и в волноводе, то все получается, волна входит в волноводный слой. Вот. Ну, здесь формула показывает. Ну вот, экспериментальное, значит, значение. Ну, мы напыляли, используя T3O5, значит, напыляли, доокисляли и получали двуокись титана. Вот. Ну, вот здесь по показателям преломления. Вот, призма, на самом деле, для необыкновенного луча имела показатель преломления где-то 2,9. Вот. Ну, то есть даже больше, чем 2,6. Вот. Здесь, значит, ну, здесь, значит, условия вхождения. Ну, вот такую призму сделали. Вот. Это, короче, мы на это где-то на полгода делали эту призму. Вот. И после того, как ввели, например, после того, как ввели излучение в призму, нужно было померить, какие все-таки потери возникают в слое. Вот. Ну, чтобы померить потери, ну, нужно было, ну, 2 возможности было. Либо ставить там вторую призму и двигать ее по волноводному слою, в одном месте померить, в другом месте померить и разницу взять. Вот. Но мы решили по-другому сделать. Так как потери, в общем-то, составляли порядка 0,4 ну, где-то 0,2-0,4 децибела. Ну, в зависимости от напыления, в зависимости от технологии. Вот. Ну, вообще говорят, что для волноводных слоев, если потери меньше 1 дБ на сантиметр, то можно их использовать, ну, в оптоэлектронике вполне, так сказать. Вот. Поэтому мы вот собрали такую установку на экране. Да, и чтобы, значит, эту призму, чтобы через призму ввести излучение, там, значит, зазор должен быть порядка, ну, четверти, ну, порядка четверти, от четверти до половины длины волны. Но это где-то составляет порядка там, ну 0,2, там, 0,3 микрона. Это очень маленькие величины, и для того, чтобы такие маленькие зазоры получить, надо очень сильно прижимать. И прижим порядка там 10 килограмм на сантиметр квадратный. Вот. Поэтому, если, допустим, без иммерсии мы сделали, надо было прижимать, ну, порядка 10-15 килограмм. Вот эта установка с винтами, она с пружинами и позволяла прижимать с такой силой. Вот. И при каком-то, вот, закручиваешь эти гайки, при каком-то усилии начинает входить излучение туда. Вот. Ну вот тут как бы. Ну и вот здесь как бы увеличенная картинка показана. То есть видно, вот входит излучение, и оно затухает. Вот. Ну, надо было померить. То есть профотометрировали эту дорожку. Значит, нужно было найти программу, которая как бы автоматически все это сделает. Вот. Ну и программа здесь, значит, вот программу нашли Гридзион. Вот. Но эта программа использует сканирующих зондовых микроскопов. Вот. Ну, используя эту программу, просто сфотографировали и мерили просто интенсивность излучения, которое распространяется вдоль этого волноводного слоя. Здесь оно был первый, значит, первый и второй порядок. В первом порядке, значит, он выходил где-то под углом 8 градусов из волновода, а при другом порядке под углом 40 градусов. Но это, в общем-то, не важно. Нам главное было определить потери на длине. Вот это как бы метрический параметр, который нужно было определить. Вот. Ну и это вот как бы картинка такая получилась. То есть видно, по волноводу проходит затухание. То есть вот затухание, там вот видно в начале где-то 0,5, в конце где-то 0,6. Но в результате при подсчете там оказалось, что, значит, на расстоянии 4 сантиметра там менялось от 0,8 до 0,55, ну и составляло где-то 0,41 децибел на сантиметр. Ну вот это как бы основная величина, которую мы хотели получить. Вот. Ну и я что хочу еще сказать, что вот эти как бы слои с большим показателем преломления, они очень интересны для необата лития, так как у необата лития где-то 2,3 показатель преломления, здесь 2,6, и можно использовать в качестве волноводного слоя на необате лития управлять излучением. То есть вот такая работа была практическая.
Thank you very much. Вопросы по-русски?
Я вот что-то немножко геометрию эксперимента не понял, значит, у вас вот призма — это согласующий элемент, а потом дальше волна, так сказать, вот постой, но у вас с одной стороны одно отношение, рефракция, а с другой стороны другое. Как тут вообще полное внутреннее отражение-то формируется? Или здесь недорисовано что-то?
Полное внутреннее отражение, ну, в слое же там. У нас здесь не волновод, мы сделали просто плоский слой, напылили.
Отражение на границах. Есть понятие угол полного внутреннего отражения.
Ну да. Ну, в призме.
С одной стороны у него один слой.
Нет, ну да, в призме возбуждается стоячая волна, согласовала. Да.
А дальше он пошел.
Ну да, ну в волноводе в самом тоже полное внутреннее отражение, с одной грани, а другой, вот там одна и бежит.
Одна грань с одним веществом граничит, а другая с другим.
Ну правильно. Ну,
какой же здесь?
Ну здесь получается здесь несимметричный волновод. Здесь получается несимметричный волновод. Так любой волновод работает за счет полного внутреннего отражения. Любой волновод. Полное внутреннее отражение. Просто он несимметричный. С одной стороны воздух, Вот. А с другой стороны, вот, ну мы вот исследовали.
Да, не хватает картинки с углами падения, да?
Двуокись титана двуокись титана напылили на стекло. И смотрели потери в двуокиси титана.
С другой стороны атмосфера.
Да, с одной стороны стекло, с другой атмосфера. Ну, получается несимметричная волна. Вот, ну что? Излучение-то идет по нему, это видно. Ну правильно, а потери...
Выполняется условие, а другой нет.
Как это? Выполняется с обоих сторон. Ну что? Ну вот видно дорожка.
Угол такой большой,
Да, от угла зависит.
отражается и от воздуха, и от подложки. Угол такой большой.
Нужна картинка была, да.
Угол больше
Так,
критического. И для
еще
этого
вопросы давайте зададим. Есть возможность.
Нет, там возбуждается вообще, вы какую хотите моду возбудите. Можете первую, может вторую, может третью. Там любую моду можете возбудить в зависимости от угла падения в призму. Просто вас смущает из-за того, что с одной стороны воздух, а с другой стороны стекло. У стекла 1,5, у воздуха единица. Ну и что? Получается несимметричный волновод. Все равно все выполняется. Вот и все. А он бежит по этому волноводу, и мы смотрим потери, как он затухает.
100%.
Всегда живу в хотите, как не было отражения.
И что?
Да, еще вопрос.
Да нет, у него просто угол, по которому по волноводу распространяется излучение.
А вы не могли бы показать картинку, где у вас ПВО призма и выводите излучение?
Почему? Почему? Углы все одинаковые. Но оба больше угла.
Вот я понимаю, что это был вколот торец волновода. Это был торец волновода.
Нет, никакой не торец, это прям на волноводе лежит призма. На самом волноводе.
А N1 чему равно?
В том-то и кайф, понимаете?
То есть вы будете не с торца.
Она лежит на волноводе, никаких проблем. Положили. С торца неинтересно вводить, понимаете? Вот замучитесь в торец вести. Поэтому этот способ положили на волновод и все.
Он не равен.
А шероховатость как вы померили плоскость?
Надо было все доклады на русском.
Ну, плоскость мы взяли устройство.
Насколько вы параллельность соблюли? У вас там, если у вас это...
Коллеги, да, я предлагаю на правах ведущего завершить дискуссию. И кому интересно, вы можете остаться и детали обсудить. Просто здесь присутствует член оргкомитета, которому нужно набежать на собрание. Мы его должны отпустить.
Оно прижимает силой 50 килограмм, может прижимать. Очень сильно. Достаточно было как 5-10 килограмм.
Большое спасибо за доклад. Вы можете остаться здесь обсудить, оставить свои контакты. И, коллеги, благодарю всех за участие. Thank you very much for the participation. Our evening session is closed, and we'll see you tomorrow.
Все 5 минут, как заряжаю, начать. Точно начать.
Честно говоря, сегодня готовиться.
Какой-то блюд, я сейчас.